Okay, good morning, everyone. Thank you for coming here for our mini colloquium on micro and nano device. We have today 4 excellent talks, as you can see in the screen, for very important people in the science and from IEEE distinguished lectures, and I'm sure that all of you like a lot. Well, let me see now. Okay, 8:05. I think you can start the first talk. And the first one is Professor Hiroshi Hawaii. From his talk is about the impact, the history, and future of nanoelectronics. Professor Hiroshi Hawaii received a PhD degree from University of Tokyo. He worked at Toshiba Corporation from 1973 to 1999, developing NMOS, CMOS, and BiCMOS, and mixed-signal LSI technologies, and also products. In 1999, he moved to Tokyo Institute of Technology and conducted the nano-CMOS research until 2020. He is currently a Vice Dean and Distinguished Chair Professor on NICU Taiwan, and Professor Emeritus at the Tokyo University of Technology, Japan. He received many awards, including all of them that you can read in the screen. He is a Life Fellow of IEEE. He served as a chair, member, editor of Academic Societies Conference Junior. He served as the president of IEEE EDS, led by Society, the director of IEEE Division, Division 1. He is an IEEE EDS eminent lecturer. Good morning for the audience, and good evening for Professor Hiroshi. Thank you for coming, Professor.
Thank you. So I like to share my slide. Oh, you.
Okay, I stopped my presentation.
Okay. Can you see?
Okay, your time. Again, Professor, please.
Yeah. Can you see now? Hello?
Yes, Fabio?
Can you see my
your
slide?
Screen.
Okay, full screen. Okay.
But not the presenter.
Okay. Is it okay?
No.
Wait. Can you see?
I can see the screen when we are in the screen, let's see, but not your presentation, Professor. Try again.
You cannot see my screen.
No, your presentation.
Hello?
No, you cannot see your presentation.
You can see my screen. Hello?
No, no, we don't see it.
Okay, I'll do it again.
Try again, please.
Okay, just a moment. Okay. Window. Can you see? Can you see? No.
No.
Professor Hiroshi, you have to click on your entire screen option.
Okay. Yeah. Last time, yes, I click entire screen.
And then you open up your slides.
Yes, I did that. I'll do it again. Entire screen now. Can you see my entire screen?
No.
No. Last time it worked very well, so I don't know why. We did a test.
It works well. Just after you select the full screen, you have to push it, the screen itself. Push the button in the screen itself. Try, please.
Now I think
Great. Now it's coming.
okay.
Okay,
Okay.
great.
Okay, sorry. Okay, can you see?
Yes, now it's
Okay,
better.
okay. So I'm sorry it takes some time.
No problem, Professor.
Okay. So yeah, good morning or good evening. So today I'll talk about the impact and history and the future of nanoelectronics. And it is the 75th anniversary of the transistor invention this year. So today I'll talk about the meaning and impact of the transistor invention, which evolved to micro nanoelectronics, and also history and future of micro nanoelectronics. So before the transistor invention, the first leap was invention of electric engineering in 1830s. That was transfer the energy and information for long distance instantaneously by electric wire. And electric power generated was transferred and drive the electric motor or illuminate electric lamp. And for the information transportation, electric telegraph was proposed for the commercial use in 1837 by Samuel Morse. And Morse code pulse was transferred via electric wire. And we can communicate with sentences instantaneously. But the electric signal decayed for long electric line. So amplifier is necessary. So amplifier was relay. And this consists of input line and output line. And for the input line, electromagnet is placed. And input pulse is magnified by switching this electric magnetic switch, and amplified pulse it appear on the output line. So the Morse code is amplified by relay and further amplified. So relay was the first amplifier, but it's only a digital amplifier and very low frequency operation because of the mechanical switch. The second leap was invention of electronics in early 1900. And what is electronics? Electronics is to manipulate electron movement as we wish for the application. Those are communication and computation. And wireless communication started at the end of 1890s, and high frequency analog and digital amplification was demanded for wireless communication. And this was realized by the invention of the triode vacuum tube 1906. This was invented by De Forest. And this is a vacuum tube, triode, and the cathode is heated and some electron is emitted. And when bias the anode side, then electron current flow. This current is manipulated by the grid bias, and we input some signal to the grid. then the amplified signal appears on the anode side. So electron current in vacuum tube is modulated by the grid potential. And triode vacuum tube manipulated electron movement for device application as we wish. So this is the beginning of electronics. And by the invention of the triode vacuum tube, electronics society started. And vacuum tube provided us radio, TV, broadcast, telecommunication, automatic machine control, etc. And vacuum tubes were the most popular electron devices until the middle of 1960s, even after the invention of the transistor. But vacuum tube, it is difficult to decrease the size, so large capacitance and long transit time. So low frequency, because of that, only a low frequency operation. And cathode is heated 1700 degrees centigrade, and it is difficult to decrease the voltage, so large power consumption. So idea is to use the solid-state devices for higher frequency and low power consumption operation. So before the transistor invention, okay, the first leap was electric engineering. I'm sorry, this is not 1830s. The second leap was the invention of electronics in early 1900. And the third leap was the invention of the transistor in 1947 and resulted micro nanoelectronics. So this is the invention of the transistor in December 16, 1947. I'll explain in detail later. So after the invention of the transistor, there's the introduction of photolithography, 1955 and 57. And also there is continuous development of semiconductor technologies. And this resulted in micro nanoelectronics. So transistor is the origin of the micro nanoelectronics. So this is a trend of a device shrinking from the relay to the vacuum tube, transistor, photolithography, IC, Mosfet, LSI, nano Cmos, and recent stacked channel sheet, CFET. So miniaturization is a new concept. And in 115 years from the triode vacuum tube invention, the electron device size decreases 10 to the 5th times. And this is, causes tremendous performance increase. Like performance increases 1 billion to 1 trillion times in operational speed, energy consumption, volume, weight, and also in cost. So I'll talk about the impact of the transistor invention and resulted micro nanoelectronics. So today, 1 terabit or 128 gigabyte SD card is available for everyone. And what would happen if we make 1 terabit memory with 1 trillion vacuum tubes, assuming these parameters? What is the price? Price is 100 trillion Japanese yen. It corresponds to Japanese national budget. And what is the weight? It is 100 megaton. That corresponds to the weight of 20 million elephants. And what would be a volume? That is 0.5 times 0.5 times 1 cubic kilometer. And this is larger than today's world tallest building. Just for one 28 gigabyte memory, okay? For the power consumption is 50 terawatt. And how big 50 terawatt is? One nuclear reactor creates only 1 billion watt. So we need 50,000 nuclear reactor. Okay. What is the yearly energy consumption? That is 4 times 10 to the 20th calorie. And that is a 2,000 of yearly global human consumption. So without the micro nanoelectronics, today's smart society does not exist. And even internet or IoT do not exist. So micro nanoelectronics was the biggest technical revolution after the electronics. So this briefly shows the trend of electronics, microelectronics, and nanoelectronics. So because of the nanoelectronics, we are going to smart society now. So I'll explain the road from the triode vacuum tube to the first transistor. Okay. And it was not an easy way. Because it is very easy to manipulate the electron beam in a vacuum tube by grid. But in the solid device case, there are so many charges, ions, or electrons, or holes. So it is very difficult to control the current from outside. Okay, so we assume that we need to ultra-thin semiconductor film. And this current should be controlled by capacitive coupling. Okay. So in 1920s to 1940s, there are many ideas of solid-state triode. They did not work because of bad selection of semiconductors and low impurity of semiconductor, low purity of semiconductor material, and lack of semiconductor physics, and no control of semiconductor surface property. In 1928, method was proposed by Lilienfeld, and 28, Mosfet was proposed. And in 1935, again Mosfet was proposed by Hale Oscar. By the way, he proposed the first idea of the double gate or nanosheet Mosfet. You can see the channel is sandwiched from the upper gate and lower gate. So this is his invention. So this is a patent of the first Mosfet filed March 28, 1928 by Lilienfeld. Okay. And copper sulfide was used as a semiconductor. And aluminum gate controlled, and gate oxide was aluminum oxide. Okay. There is a triangle depression and very thin area here. And the current which flows very thin area is controlled by the grid bias. This is his idea. However, there is no experimental record by Lilienfeld. And later, J.B. Johnson did an experiment. But because of copper sulfide is not a suitable material, it's a metallic, there is no current modulation at all. So his device is just idea and did not work. Okay. The first experimental record of FET, actually Mosfet, was published by von Hirsch and R. Paul in 1938. So they used KBR rectangular parallelepiped. And it's a very large, some millimeter scale. And this is a very wide band gap. It can operate at high temperature, 490 degrees centigrade. And amplification was only the VG equal from 0 to 13 volt. After that, there is leakage of VG because it's a Mosfet. And amplitude was 20, but it only operates at sub-hertz, so it was not good at all. Okay. Later, in 1940s, 1945, William Shockley of Bell Laboratories thought of Mosfet idea independently from Lilienfeld and Oscar. And this is his idea of a Mosfet. It's almost same as today's Mosfet, but it's only accumulation mode, not an inversion mode. Okay. He did an experiment, but no current modulation at all was detected. Okay. The reason is because of the surface state, and charge trapped at the surface state shielded the electric field from the gate electrode. They continued the research of current modulation, and 2 years later, November 17th, 1947, Brattin and Livni found electrolyte, it's a distilled water, compensates the surface state charge and thickness of the inverted p-type silicon layer was changed by the applied voltage. Okay? So this was confirmed by the photovoltaic voltage between a P inverted and N substrate junction. So this is a first result of the potential control of the surface by the gate voltage. And November 27th, 1947, Bardeen proposed to measure the current injected from the point contact metal. And current modulation by control electrode voltage was confirmed. So control electrode is located inside of the electrolyte, okay, liquid. This is a ring shape. And by changing the voltage of control electrode, the current modulation was detected. So current amplification 10% and power amplification was found, but no voltage amplification. Because of the slow response of the electrolyte, operation frequency was less than 10 Hz. December 11th, 1947, Brattin and Bardeen changed silicon to germanium and replaced electrolyte with germanium oxide. So this is a germanium oxide layer. Okay. For the high frequency operation, electrolyte was not good for high frequency operation. But in reality, it happened that oxide did not exist. Oxide was washed out by water before the gold plate deposition. And they found by happening that input signal given from the control gate was amplified at the output voltage. Okay. So voltage gain was observed. However, there is no power gain. So December 15th, Bardeen proposed to put two electrodes with a distance of less than 15 micrometer in order to increase the power gain. And this is a real structure which Brattin made. So there is some plastic triangle and gold foil was put at the surface, and at the apex of the plastic triangle, the gold foil was cut with a separation of 20 micrometer. And next day, December 16, they observed power gain 1.3 and voltage gain 15 at 1 kilohertz. So this is the invention of the point contact transistor. Later in commercial device, the plate tungsten wire was used as the electrode, as shown here. I'll explain the mechanism of point contact transistor. It is not a surface current. Okay. So there is no bias at the emitter. Reverse current flows from the collector to the substrate. The collector bias is about 40 volts, just for example. And when the emitter is a forward bias, about 0.2 volt, the huge amount of hole flows from emitter to the collector. And this hole flow changes the potential of the near the collector. And potential change increase the injection of the reverse biased Schottky barrier. So the current gain was 1.3, and voltage gain was 62, and power gain was 80 at 1 kilohertz operation. So this is the transistor operation of the point contact. Okay. And this is a typical commercial device produced by RCA later 1954. And this point contact device was used for many applications in early 1950s. But point contact was not stable, and Shockley thought of junction bipolar transistor, so sandwich structure of NPN, in January 23rd of the 1948. So it is less than 1 month of the invention of the point contact transistor. Okay. When the emitter when the base bias is 0 volt, there is no current flow from this junction. So there is no current flow from emitter to collector. When the base is biased 1 volt, there is a current flow of the PN junction of emitter and base, and electrons injected the base will flow into the collector via drift. Okay. This is a mechanism of the junction transistor. And the first junction transistor was made 1951, as shown here. So base contact is a very narrow region, so it is a little bit risky, but this commercial device works very well. And actually, this is used for Sony's radio receiver. So 1950s, 60s, point contact transistor was eventually replaced by junction transistor. Transistors are used for radio, machine control, military widely. And the key semiconductor technologies were developed in this period: photolithography, implicit diffusion with oxide mask, germanium silicon crystal growth and purification, cleaning technology, epitaxial growth, and ion implantation, all developed in this period. And as you know, the first integrated circuit was made 1958, but this is just a bonding wire for the connection, so it is not good. And practical monolithic integrated circuit was made by Robert Nice in 1959. And he made the flip-flop circuit using this technique. So I'll talk about the road to Mosfet for the successful operation. Because the first purpose was to realize the triode, semiconductor triode. So on December 26, 1947, the Pearson of the Shockley group did a Mosfet experiment. They used a quartz as a substrate and evaporated the gold and the semiconductor thin films to both sides. And they applied 30 kilovolt, and they detected the current modulation for the first time, but it was about the 10,000th times smaller. So due to the large density of interfacial fixed charge, the conduction was very, very poor. So this is not a practical at all. And in 1953, inversion type of the channel was experimented by W. Brown of Bell Laboratories. But the gate voltage was applied from the backside. Anyway, this is the first trial of the inversion type of the FET. And in 1959, M. Atola et al. Of Bell Laboratories found that SiO2 gate film growth by the high temperature oxidation of silicon is stable without a slow state. And stability of the gate film by high temperature oxidation of silicon was much better than those anodic oxidation and deposition. So next year, the Dr. Khan Atola used the thermally grown silicon dioxide as a gate insulator. By that time, the quality of semiconductor improved very much. And they found the good operation of the Mosfet. And these are the measured results of the Mosfet published in 1960s in the conferences. So from 1960 to 1968, most ICs were supposed to replace bipolar ICs because of the easiness of the integration due to the surface devices. But it did not happen until 1969. Most integrated circuit trials started in early 1960s. However, because of the instability problem due to the various charges in the gate oxide and interface, most of the production was failed. Also, yield was extremely low at that period. In 1965, most IC processors for the calculator, 100 Mosfet per chips, were produced by General Micronics, but it failed. 1965, 64-bit SRAM, including a 400 Mosfet per chip, was produced by Fairchild, but they failed without no full-bit operation. From the middle of 1960s, small or medium-scale MOS ICs, standard logic, or shift register was in the market. They use aluminum gate PMOS technology, but are not a good ICs at the time. As you know, at that time, there are so many different charges, like a mobile ion, or oxide trap charge, or interfacial charges, or what existed. So they are very confused, and there is no solution to suppress these charges at all at the beginning. But a trial of the integral circuit was made already in 1963, using a MOS array, and General Electric produced 16 transistor logic clock as an experiment, as shown here. And this is the first MOS memory, first SRAM produced by Fairchild, but they did not work with a full bit operation because of the very bad yield at the time. From 1969, instability problem was solved and yield improved, and new technology developed silicon gate, low-cost isolation, reflow, ion implanted channel, etc. This new technology was not used by all companies in early 1970s, but some companies used. And most LSI with more than 1,000 Mosfet in a chip started. And 256-bit SRAM, 1 kilobit DRAM, and 4-bit MPU was produced by Intel. And many processors for electric calculators with aluminum gate technology was also produced by many other companies. This is an example of the LSI produced by Intel 1969, 1970, and 1971. And I also made Toshiba's first NMOS LSI in 1975. At the time, the structure was very, very simple, and they have only 8 mask layers. And material is used is only a very limited. Only several materials are used. And many young ladies produce the Mosfet. And this is a Toshiba DRAM chip trend from 1 kilobit to 64 kilobit. I also participated in the fabrication of a 64 kilobit DRAM. So since 1970s, LSI downscaling continued 50 years. So what would be the limit and what would be the future? So what's the limit of downsizing? So there is the ultimate limit, that's the distance between the atoms, that is 0.3 nanometer. And below 0.3 nanometer, okay, there is no physical structure. So there is no picoelectronics anymore. Nanoelectronics existed, but no picoelectronics. But before reaching ultimate limit, there is a fundamental limit. That's a direct tunneling distance. And below a direct tunneling distance, there is no insulation or no switching of the devices. But before reaching a fundamental limit, there is a practical limit. The practical limit is a demerit by downsizing. Okay? So it is expected that the practical limit is about 10 nanometer or maybe sub 10 nanometer. And below there is no commercial device. Okay? Please be careful about the technology node or commercial name of the logic nano CMOS, such as 7 nanometer or 5 nanometer technology. They are just inflated names. Recent years, CMOS technology node name have nothing to do with the real physical sizes. It is a very bad custom of logic CMOS industry. So IRD's 2020 roadmap shows that a commercial name or technology name continue to decrease to 0.7 nanometer with a ratio of 0.7 times. However, in a gate length, okay, 2020 18 nanometer does not decrease so much. And in a 2034, it stays at 12 nanometer. And metal wire pitch also. So it is nothing, 0.7 nanometer technology has nothing to do with the real size. Okay? 2 nanometer, 3 nanometers also. So let's think about what is the reason for the practical limit of the downsizing. So there are 2 reasons: transistor leakage current out of stage, and resistance increase and reliability degradation of the interconnects. The limit is supposed to be supposed to be 1 to sub nanometer. So it will not go to deep sub nanometer. So limit is very soon now. And cost and lithography and gate insulator thickness will not be the primary reason of the limit of the downsizing. Okay. I'll talk about the leakage current at off stage. There is a 4 component: punch through, direct tunneling, subthreshold, gate insulator leakage. punch-through current is like that. So there's a positive potential region near the drain. And when we decrease the gate length, this positive potential region touch to the source, and immediately electron flows to this potential positive potential region and reach the drain. This is a punch-through. Punch-through is suppressed by the multiple gate structures, as shown here. So recently, nanosheet structure is supposed to become a future device. And the second component, direct tunneling between the source and drain, is negligibly small with a gate length larger than 3 nanometer. So it will not limit the downsizing of the gate length in the region of 1 to sub-nanometer. So this is not the limiting factor. So how about the substrate leakage? So ideally, the substrate region, there is no leakage current. But in reality, there is an exponential component of the leakage current. What is the reason? Because the energy distribution of the electrons and source is governed by Boltzmann statics. And the energy which have a higher than a surface potential, the component of the electron whose energy is higher than a surface potential will diffuse into the channel region and drift into the drain. So this is a substrate leakage current. So it depends on the potential barrier between the source and channel. And by scaling, threshold voltage should be decreases, and potential should be decreases. So substrate leakage current exponentially increase. So this is a problem. And when we decrease the threshold voltage 0.3 to 0.15 volt by scaling, the leakage current when gate voltage 0 volt increase 1,000 times. So subthreshold leakage limits the downsizing. Okay. So how about the gate insulator leakage? It does not limit the downsizing by using so-called high K direct gate. Okay. We can increase the physical thickness by 5 times if we use the K value over 20. And Intel already used the hafnium-based oxide with EOT is 1 nanometer in 2007. Okay. And also I did the experimental work of 0.4 nanometer EOT devices, and leakage current is 10 times smaller than the required value by ITRS. Even EOT is 0.4 nanometer. So gate leakage will not limit the downsizing. However, long-time reliability such as PBTI will limit the EOT around 0.9 to 0.8 nanometer at this moment. If we want to decrease the gate length into sub 10 nanometer region, reduction of the EOT to 0.7 to 0.6 are required. So this would be very difficult for the mass production level. So in the reliability concerns, maybe gate oxide thickness will limit the downsizing. Okay? So I'll talk about the near future in 15 years. We still continue the effort of downsizing about 10 years. Let's take a look at the IRDS 2020. Okay. The gate length and metal wire pitch will reach a limit in 2028. Okay, at 12 nanometer and 16 nanometer. But we can keep the Moore's law by the integration to the three-dimensional vertical directions. And we can keep increase the density of SRAM cell and also a 2 NAND logic gate as shown here. But problem is a heat generation and cost increase as shown here. So sometimes it will limit the 3D integration limit, maybe in 10 years or so. Okay. Already 7 stacked channel nanosheet Mosfet was published a few years ago. And also, in case of the flash memory, 200 stacked layer is expected. And also, in a die-level three-dimensional integration is proceeding. So, in 15 years, still continue the effort of the, we will do the effort of the downsizing. However, the downsizing will reach the limit in 10 years due to the off-leakage of Mosfet and resistance increase and reliability degradation of metal lines. By 3D integration, we can increase the integration and keep the mother low. However, 3D integration will reach its limit in some future due to the cost and heat generation, which are created by huge number of the devices with a small footprint. Let us take a look of the front-end R&D activity published at IDEM 2021. And progress of 3D trend of Mosfets are more aggressive than IRDS. And we will agree, we have so many things to do in future. And Mosfet structure will evolve from fin, nanosheet, fork sheet, and CFET. Okay. N and P Mosfet are integrated vertically. And Intel already published 8-layer nanosheet, and they decrease the footprint of a Cmos gate by half. And also National Taiwan University published 8 layers of nanosheet MOSFET with P MOSFET. And there is also a wafer level or die level integrations. And also many aggressive research to replacing the wire materials by many different metal is going. So there are many things to do for the 3D integration and also the downsizing. Okay. So what will be after reaching the limit of the 3D integrations? Don't worry, no problem at all. The demand for LSIs and semiconductor devices will keep increasing in the future intelligent smart society. What kind of demands? More supply for LSI and semiconductor devices, more optimization for each applications, new functions, and the price decrease. So we need more engineers for the above. And finally, I'll talk about the future towards the 22nd century. And we have to think about introducing a biosystem. And as you know, mosquito brain and dragonfly brain is much efficient than today's AI computer system. And for the neuron system, okay, the electric pulse is only transmitted when it is active. Okay. And the electric pulse height is only 100 millivolt, and frequency is less than 1 kilohertz. So extremely low power consumptions compared with the AI system. Okay. And there is no off-leakage current because in the off state, there is no pulse at all between the synapses. For the interconnect, neuron has more than 1,000 connections each other per neuron, and much efficient for the processing. For the Mosfet case, the connection is only a 2D, so only several connections per Mosfet is available. If we did 1,000 connections per Mosfet, very huge extra area is necessary, and also very huge parasitic power consumption is necessary. So it is impractical. So biosystem or brain is much more efficient than AI on the semiconductor. But why human brain cannot win AI games? Because human brain is not designed to keep concentration for only one thing for long hours, and the brain loses interest to do the same things for long hours, then get tired or sleepy. And the human brain needs rest and sleep, and the human brain cannot remember huge volume data accurately. But the problem is AI on semiconductor consumes huge energy only for one thing, and thus cannot treat many items which human brain can do easily. Okay, human brain cannot keep concentration for only one thing for long hours and cannot remember huge volumes of data. So the solution is to help each other or cooperation between the AI and the brain. In order to make the biosystem more reliable, we need to develop direct communication between the semiconductor and the brain. And this means we'll be able to communicate directly with the brains of dogs and cats in the future. This is not SF world. Already we can display the image which humans see in the brain using a blood sensor and AI techniques. So machine cannot compete with the dogs, drug sniffing, hunting, threading, policing, and rescuing, seeing eye, stock marking, and stock farming and other pet. So we might use birds, insects, rats, fish for surveillance and maintenance of tunneling, bridge building, etc. from air, surface, earth, water more efficiently and safely and for long hours than a drone or a robot. We traditionally use animals for food, labor as a friend, and also as a friend. We do need human society consensus how to treat animals and insects considering the ethics. At the same time, we also need to improve the semiconductor devices by learning from biosystems, such as implementing algorithms of bio and imitating physical structures of the bio. So in conclusion, 18th to 19th century, mechanics controls the society. 20th to 21st century, electronics and mechanics control the society. From the 22nd century, bionics, electronics, and mechanics will control the society. So we have experienced exciting period for the development of electronics and micro-nano electronics in the past 115 years. Next 100 years will be more exciting period with the cooperation of bionics and electronics and mechanics. So thank you very much for your kind attention. Okay, I'll go back. I'll cancel the share. Okay.
Professor, thank you very much. An excellent talk. You talk about the history and then the future and everything. It was excellent. Thank you very much for your talk. And we are waiting for some questions from the YouTube. While that, I'd like to make your first questions. Professor, what do you think to be the real limit of the, let's say, the last nanotechnology node? Will be the technical problems or will be the financial problems?
Oh, it's a technical problem.
Probably technical problem.
As I told, the leakage current is one thing, okay? If there is leakage current, we cannot switch off the device.
Understand.
And also for analog application, we could use, but still that consumes a huge power. So because we make so many devices, so the price per device is decreasing. Yeah, because so huge a demand from the market, the price is not a big issue.
Understand. Thank you, Professor. In the chat, we have one question. May you
Yes.
have a look on that, please?
So while the transistor size decreases with new technology node, the wafer area increases. Is increasing the wafer size a valid strategy to reduce the height? Oh, I think it will not happen because changing a wafer costs a very, very huge. So many people thought about 450 millimeter wafer, but it will never happen.
Okay, Professor. Professor Jacobs also make a question, please.
What do you think about the quantum computing? That's a very interesting. Okay, but at this moment, I do not know because there is a huge noise of a quantum qubit, and we have to decrease the noise. With increase of a qubit, the problem is how error bit, how to screen out the error bit. And that's what I think. Yes. And second thing is, of course, it cannot be used as a mobile device. And it is only probably for a central computer. So maybe, so I'm not sure, but application is also limited. But it is very, very important to keep the research. Okay, that's very important. Not abandon. We do not know what will happen in the future.
Okay. Thank you, Professor. Okay, in the chat, there is many people. Great presentation for you, and I'd like to thank you very much. If someone have another question, you can send direct to Professor Hawaii. And thank you very much for coming and for stay with us, Professor. It was a great.
Yeah, thank you very much. So I'm sorry that I consume time.
No,
because my connection was
was
excellent. Connection was not good. So.
The next time perhaps you can do it presentially here in Brazil. Thank you.
I was a little bit hurry my presentations. I'm sorry.
No, it's great. Thank you, Professor. Bye.
Yeah, thank you. Okay.
Let's move to the second one. And okay, the second presentation is about the tunnel field effect transistor and its application as highly sensitive and fast biosensor. And this paper will be given by Professor Manoj Saxena from Deen Dayal Upadhyaya College, University of Delhi, Nova Delhi, India. Professor Manoj Saxena received a PhD degree from University of Delhi in India. He is currently professor at the Deen Dayal Upadhyaya College, University of Delhi, India. He has authored and co-authored 315 technical papers in international journal. Put in presentation format, it's better. And journals and conference procedure, and has delivered 30 EDS LED Device Society district lectures. His areas of research are mathematical modeling and TCAD simulation, and non-classical Mosfet, tunnel FET, and ham designs. He is a fellow of the National Academy of Science in India, fellow Institution of Electronic and Telecommunication Engineers in India. He is currently a member of IEEE LED Device Society Board of Governors and Associate Editor-in-Chief IEEE EDS Newsletter, IEEE EDS Distinction Lecturer since 2016, and Chair of EDS Dielectric Chapter since 2002. Thank you for coming, Professor. Please, it's a pleasure for us to receive you here.
Oh, thank you, Martino. Just let me know if my screen is clearly visible.
Yes.
Yeah, is it good to go?
Yes. Yes, I can see.
Okay, yeah. So thank you very much, Martino, and all the executive officers of the EDS South Brazil EDS chapter for inviting me to be part of this NQ on micro and nano devices. And I'll be talking today on tunnel field effect transistor and its application as a highly sensitive and fast biosensor. Let me just use a pointer also. Yeah. In the next 45 minutes, I'll be covering a little bit about the IEEE Electron Device Society, with which I'm associated for more than 15 years now. And as I am the chair of the ad hoc committee for the celebration of the 75th anniversary of Transistor, which Professor Hiroshi Awai has already highlighted, I'll be covering a little bit about that, related to the non-classical Mosfet architectures, leading to tunnel FETs and some of the emerging architectures of tunnel FETs, which I'll be highlighting especially for the young EDS student members who may be listening to this talk through YouTube. The Electron Devices Group, that is IEEE EDS Group, became the IEEE Electron Device Society on February 17, 1976. And this is the 46th year, and very soon we'll be celebrating the 50 years of the IEEE Electron Device Society, which has been promoting the excellence in the field of electron devices for the benefit of humanity. And the main EDS mission and vision is to foster the professional growth of its members through these three different areas. One is publishing, open access, EDS supported conferences, journals like TED, EDL, IEEE JFlex, JLT, and so on. The webinars, DL talks, MQs, which you are currently listening to, the technical recognition in terms of awards and student fellowship for the EDS student members. And these are the typical field of interest of EDS, which covers nearly all aspects of engineering, physics, theory, experiment, simulation of electron and ion devices, and as well as for emerging materials. And this is how the EDS is spread all across the globe. There are more than 230 chapters. This figure has to be updated, as in the recent board meeting, we have came to know that around 20 plus chapters have been formulated in last 2 years, that is in the pandemic itself. And there's a huge number of around 9,000 members, which are there in region 1 to region 10. So that's a very fast growing society in terms of the IEEE. Now, the students who are the PhD scholars who are listening to this talk, there's an opportunity in terms of student fellowship, which is 1-year fellowship. And there are 3 such fellowships which are awarded, and one for each geographical region, that is America, Europe, Middle East, Africa, and Asia Pacific. And on selection, you'll get 5,000 USD and also necessary funds to visit and to attend the IDM conference over there. The eligibility condition for the students is that he or she must be an EDS student member at the time of nomination and be pursuing a doctorate degree within the EDS field of interest on a full-time basis. And it's a highly competitive fellowship, and the basis for judging is the demonstration of his or her significant ability to perform independent research in the field of electron devices. For those master's level students who are attending this talk, there's an opportunity for all of you, again, a 1-year fellowship and a USD 2,000 US dollars with a pledge for all the students to be presented by the dean or the department head of the students enrolled graduate program. And the basis for judging on the EDS student member who is going to apply for this is the demonstration of his or her significant ability to perform research in the field of electron devices and a proven history of academic excellence in engineering and or physics, as well as involved in undergraduate research and or supervised project. So this is a good opportunity for master's level student also. There's also opportunity for the undergrad student fellowship, scholarships which are there, and there are 5 such in number, spread across for region 8, 9, and 10, and 2 fellowships in region 1 to 7. USD 1000 to be presented again by the dean or department head, and the candidate must be an EDS student member, a full-time undergraduate student in an engineering program, and should have a proven record of microelectronic course which has studied with good grades and is highly motivated to study and perform research in the field of electron devices. So these are 3 opportunities which are there for the EDS student members. And the EDS also supports the chapters through summer schools, through funding through MQs, and also there is an industrial placement which is taking place by the EDS Society. So on behalf of the IEEE Electron Device Society, I would like to invite all of you who are non-EDS members to take up EDS membership, and that will be a good gain for the society itself. So Professor Hiroshi Awai has already highlighted that this is the 75th year of invention of transistor. Like we have already, we are aware of this fact that the year 1905 is well known as the miracle year because Albert Einstein published 4 papers that changed the laws of physics, and they were significant contribution to the foundation of the modern physics. Similarly, 3 months, that is November 1947 to January 1948, were the 3 magical months that paved the way for modern day electronics. And the credit goes to the 3 famous physicists, William Shockley, John Bardeen, and Walter Brattain. And Walter Brattain and John Bardeen managed to make the first point contact transistor December 16, 1947, followed by William Shockley's demonstration of the first junction transistor in 1948, for which all 3 of them, they received the Nobel Prize in Physics in 1956 itself. The EDS Society has decided to celebrate the year 2022-2023 as a 75th anniversary of the transistor. A special page has been created on the EDS homepage, and I invite all of you to kindly visit to this page where all the developments and all the programs related to the 75th anniversary of transistor are being posted over there. And as part of the ad hoc committee for the 75th anniversary of the transistor, we will be organizing several talks at conferences, MQs, technical articles, and newsletters. Our webinar series shall be there, which is part of the various activities which this committee is going to take forward and to provide technical information and education to enlighten all its EDS members. So that's a big opportunity for us and for all the EDS chapter to organize as many activities as possible so that you can compete in the Best Chapter Award from your region, and that will be a good contribution from your side. Moving ahead, Professor Awai has already set the stage for me that what is the need for device scaling, be it in terms of improving the package density or in terms of higher circuit speed of operation. But these 2 things are possible only when we will be getting along with some material and structural innovation if we wish to continue the matching trend of the scaling as well as with the performance requirement, which is very difficult when we are scaling down the device dimensions below 90 nanometer itself. Some of the short channel effects or the scaling issues which Professor Awai has already covered, I'll be skipping those part. But the 5 major problems which we see, one is obviously the offstate leakage current, the high values of the Dibble values which we see, the poor subthreshold slope, channel length modulation effect, and the velocity saturation effects. These are the 5 major challenges which we face when we are going in for scaling down the conventional MOSFETs. Now, what are the ways ahead? How can we look out for an alternative approaches, that is what after the planar MOSFETs? So one of the ways is to go in for a gate electrode work function engineering, whereby we are no longer going for a single material gate MOSFET, whereas we are going in for a dual material gate MOSFET, which problems which are associated with gate oxide engineering.
Professor Saxena, just a minute, you have a problem with your audio. Your audio cannot hear you.
Okay.
Have a look in your audio, please.
Sure. Am I okay now?
No, no, it's okay.
Now it's okay. Okay, I'll just switch off my video for a while. Maybe that may be one of the issues. Yeah. Okay, can you see my slides now?
Yes.
Okay, fine. So the other issue is related to the gate oxide engineering. Was one of the ways where we can have high K, low K systems. The other three approaches are, one is going in for the lateral channel engineering, going in for like a lightly doped drain MOSFET, a halo type architecture, a pocket implant, a dielectric MOSFET, dielectric pocket MOSFET. A substrate engineering going in for an SOI or silicon on nothing. A gate electrode engineering where we are going to have a dual gate or a split gate or a double gate MOSFET. Now, taking a cue from all of them, there have been several other designs which have been proposed in past, wherein a combination of lateral channel engineering with substrate engineering has been reported, along with the lateral channel engineering and gate electrode engineering has also been reported. So I'll be touching upon some of them in the next few slides. The first one being the lightly doped drain MOSFET, which prevents the electric field penetration from the source and the drain side. So as you can see, these are the LDD extensions, but they have a disadvantage of increasing the series resistance due to the low doped channel region near the source and the drain. In order to overcome that, halo or a highly doped drain MOSFET was proposed, where it creates a non-uniform potential under the channel region and can suppress the depletion region in the channel leakage current. But it has its own disadvantage that it has an increase in the junction capacitance, and it also leads to an increase in the threshold voltage, which thereby reducing the drain current also. So in year 2001, in order to overcome these shortcomings of implanted pockets of LDD and halo, a new concept of dielectric pocket embedded was proposed. And whereby these dielectric silicon dioxide, these dielectric pockets, they were acting as a lateral diffusion stopper for the heavily doped source and the drain region itself. And this significantly lowers the electric field and it gives better gate controllability over the channel region itself. But it has its own demerits. And the first one being that its drive current for the ISC, ISC also stands for insulated shallow extension or a dielectric pocket MOSFET, was low. And this actually leads to a reduction in the transconductance, and also the leakage current was pretty high for this bulk MOSFET design. So clubbing that with these little bit of substrate engineering, going in for an SOI type structure, one can see that we can reduce the leakage current from the itself. At the same time, another approach was reported, which was called as the silicon on nothing, that is an empty space in silicon, and whereby the thickness of this paradoxide was scaled down from 400 nanometers to 10 nanometers or so. And even the silicon dioxide was laced with the air. So you can have an ESS technique, and that's a very good paper which was reported in IEDM in 1999, how to the formation of empty space in silicon induced by silicon surface migration. So those of you who are interested in getting into the Songshan technology of silicon on nothing, it's a very good paper as a starting paper to read upon. And it has its own advantages, this particular structure, be it using the back channel coupling between the source and the channel and the drain and the channel itself. And it also helps in reducing the subthreshold slope and thinning of the channel region, which leads to enhancement in the gate controllability. So if we club these various designs in you can see that we can have an insulated shallow extension silicon on nothing MOSFET. So a lot of work has been carried out on these three different architectures in between the year 2000 to 2010. And but these devices, they suffer from a major problem of the poor on current driving capability for that. So that's the reason why we have to go in for new device architectures, where the prima facie objective is to suppress the leakage current, and also that the leakage which occurs away from the channel surface, how to get rid of that. One of the options which we have already discussed is related to the paradoxide or using an empty space in silicon. The other approach is going in for a double gate design, which helps in improving gives us a higher driving current, and due to higher current mobility associated with it, because of uh, the body doping has been eliminated in comparison to bulk MOSFET. During the same time, in 1990s, uh, another architecture was proposed that was a fully depleted lean channel transistor, a delta transistor, which is, as you can see, it's a tri-gate type architecture. And later on, it transformed into a folded channel MOSFET, which is the first N-channel FinFET design, which was reported in 1998. Moving forward, in 1999, a first P-channel FinFET was reported. In 2001, the device dimension scaled down to 15 nanometer FinFETs, 10 nanometers, and finally, in the year 2011, Intel made a big announcement that what is called as the most radical shift in the semiconductor technology in 50 years. So when all this was going on, one major problem which is associated with the conventional MOSFET always remain, and that is the limitation of the subthreshold slope value of 60 millivolts per decade at room temperature itself. So that is the point where one has to look out for new devices, new device architectures, energy efficient devices, new functional devices, and a whole plethora of devices have been there in last 2 decades. So due to paucity of time, I'll not be touching upon each one of them. However, I'll be focusing on the tunnel FETs, the tunnel field effect transistors, which has a very simple structure for all those who have a good background, sound background of MOSFET, and also what Professor Hawaii has already covered. The only difference between a conventional MOSFET and a tunnel FET is that first of all, it's a reverse bias gated pin type architecture, and that is the source and the drain, they are opposite, unlike the MOSFET itself. And the current conduction mechanism is no longer the surface conduction, but it's a junction phenomena which is taking place at the source channel interface itself. So this is the energy band diagram on the right hand side. You can see when the off state, the tunneling barrier is pretty large, and as a result of which the leakage current is extremely low. And once the device turns on, then due to the quantum tunneling which takes place between the source channel interface itself, so you'll find an abrupt turn on of this particular device. And that's the main reason why when we have to look out for, first of all, the power supply scaling, and as we have to move forward in last 5 to 10 years, a lot of research has been focused upon looking beyond the CMOS devices, and that's where the focus has been shifted to tunnel FETs for various devices and application. And one has to do a fair comparison also. So if you can see on the left-hand side, this is the IV characteristics for a bulk MOSFET or a multi-gate MOSFET, along with a high mobility 3.5 silicon germanium, and as well as a tunnel FET. And one can see clearly that the steep off-on transition and the lowest I-off associated with the tunnel FET gives its natural advantage over the conventional MOSFET designs, as we are going in for low voltage and high sweeping switch operations itself. Comparing it with the different channel materials, be it silicon, germanium, or indium arsenide, and so on, the two main important factors, one is the tunneling length and the other is the tunneling rate. So as one can see that the tunneling length for the case of the silicon, uh, as you can see, it is from 40 nanometer and it scales down to 4 nanometer or so. But if we do a little bit of channel engineering and we go in for uh, different channel materials, it can be low as 3 nanometers and so. So this helps it's a beneficial effect in terms of giving us a higher tunneling rate and due to a shorter tunneling length in a heterostructure TFET. So these two advantages helps in further improving the subthreshold slope and the on-to-off ratio for the tunnel FET. So way back in 2009, one of the experimental results reported the highest ion-to-off ratio at that time, 10 power 7. And the off currents and picoamps and low on currents is a major problem associated with tunnel FETs. As you can see, it's only in microamps. So in comparison to a Mosfet, there are certain key advantages, be it lower leakage current and the subthreshold slope is less than 60 millivolts per decade. But the major challenge, like I've just highlighted, is the drive current, and it is low as compared to MOSFET. But there is a possible solution, and that is that instead of having a PIN structure, if we go in for a Pnpn architecture, that's a tunnel source architecture. But in order to have an N-type layer closer to source and channel itself, so we need a very high dopant abruptness, and less than 4 nanometer decade is required to maximize the junction electric field and to achieve a high on current itself, which was again a major challenge. But in the year 2010, an experimental demonstration was made wherein the dopant abruptness for 1 nanometer per decade near the tuning junction was proposed, and it was thereafter being extensively used for getting into this particular design. The other problem associated with the tunnel FET is the ambipolar behavior, and how to suppress the ambipolar behavior. There are several ways. One is by going in for an underlap drain or lowering the doping on the drain side, or going in for a smaller bandgap material in the source and a larger bandgap material in the channel region. That's the heterojunction. So these are ways by which we can overcome the ambipolar behavior of the tunnel FET. So what are the possible areas? Although the tunnel FET gives us a lower drive current, but a good high on to off ratio actually gives it, makes it a really good choice for biosensing application. And other than being a high on to off ratio, one is the abrupt turn on and adjustable turn on voltage. So these are the two other factors which actually motivates anyone to go in for or look out for and application of tunnel FET in the biosensing application. Now, for all those who may not be well accustomed to the biosensors and what are the label-based and label-free, so next few slides are prima facie focused to the non-experts in this area. So there are, for the biosensors can be classified into two types. One is label-based and label-free. So we'll be discussing about the label-free detection because it is suitable for the target molecules that are not labeled or where they are not easy to tag. So it may allow any complex to be screened with minimal assay development. So that's the major advantage of going in for a label-free detection. And other than that, it also gives us a detailed information on the selectivity, affinity, and in many cases about the binding kinetics and thermodynamics of the biosensor itself. Now, the label-free biosensors, they're also further divided into two types. One is optical and the other is non-optical based. And non-optical based is where we are more interested right now, as the label-free field effect transistor-based biosensor falls into the category of non-optical based biosensor. And they have three major advantages. One is the high sensitivity and low sample consumption and low damage to the analytes. Other than that, they also have an ability to directly translate the interaction of the analytes that takes place at the surface of the FET into a readable signal. So these are the certain advantages which actually motivated our group to start working in this direction about 10 years ago and using this tunnel FET design for the biosensing application. So again, this is a very good review article, Progress of New Label-Free Techniques for Biosensors, published in Critical Reviews in Biotechnology in the year 2016. For those of you who are new entrants to this area, who have keen interest in learning the label-free techniques for biosensor, so that's a very good review article for all of you to read. The basic concept for a biosensor based on FET is the working principle, as you can see on the left-hand side. It's a dielectric modulation. So we have a cavity region at the source as well as at the drain side. So this cavity has been edged out, and here the biomolecules, they are hybridized. So we have to compare the empty cavity with the one which is filled with biomolecules, and post-hybridization, the dielectric constant is going to change in this nanogap cavity, and this leads to a change in the gate capacitance as well as it leads in the conductance of the channel itself. So for example, if we see it, the first one, the one which is represented in black, this is before the etching part, and the threshold voltage for this DMFET is 0.44 volts. And post etching in the cavity region itself, one can see that the threshold voltage has changed to 0.18, and post hybridization of the biomolecules in the cavity region, again the threshold voltage has been shifted. So this shift in the threshold voltage along with the shift in the on current or the drive current can be as one of the ways by which we can detect the presence and absence of the biomolecules for neutral biomolecules. Similarly, we have to check whether the same approach can be extended for the charged biomolecules also. So we started our work, that's in the year 2012, where the first report on tunnel FET biosensor was reported by our group, and the credit goes to this EDS student member. And here I would like to highlight that the talk is primarily based on the work carried out by our group and by the students, the EDS members, be it undergrad, postgrad, or research scholars, which have actually paved way for looking out for this particular the device for the biosensing application itself. So two months later, another group by Kaustav Banerjee and Deblina Sarkar, they also reported something similar based on the complementary FET and the TFET design. And both the works which have been carried out, they were more focused through the TCAD studies. We extended the study and we developed a full analytical model for the dielectric modulated tunnel FET, and that was published in the same year in October 2012. So these three papers, the one in EDL, subsequently in APL and TAT, it actually revolutionized the way the people has to think as an alternative architecture, tunnel FET as an alternative architecture for the biosensing application. So it worked out on a very simple concept that a cavity is edged out in the gate oxide region at the source side, because for a PIN architecture, only the source side cavity is considered, being it's a junction phenomena. And as the PIN TFET has a disadvantage of low drive current, so we considered a Pnpn architecture. This is a schematic of that. So this is the source, and this is an N-type layer, and this is the channel. So the channel is divided into three parts. The first one, that is in light blue, region 1, it is the N-type. Region 2 is beneath this cavity, but that's an intrinsic channel itself. Region 3 is beneath the gate oxide, and that's also the channel region. So this is the Pnpn architecture, and region 1, which is heavily doped. And we had also an interfacial layer of 1 nanometer, and the cavity length is considered to be 100 nanometer. and the 30 nanometer, and the gate length is 100 nanometer. So where the gap thickness is 10 nanometer, 1 nanometer being covered by the native silicon dioxide itself. As the gate capacitance in the nanogap cavity is going to change, so that is going to be translated into a shift in the threshold voltage as well as in the change in the drive current. And the biomolecules, the neutral biomolecules, when they are present in the cavity region, it actually leads to an increase, the decrease in the tunneling barrier width. And in case the biomolecules are charged, that is, they are negatively charged biomolecules, then there is going to be an increase in the flat band voltage, which reduces the effective gate bias in the cavity region. How to simulate this using a TCAD? So we varied the dielectric constant in the cavity region. One is when it's empty cavity, free air, from 2 to 10, and the charge density of the DNA is in microcoulomb range. So we considered a negative charge density of minus 10 to the power 11 centimeters square to minus 10 to the power 12 per centimeter square. And this helped us in creating a generalized analytical model for this design. And we solved the Poisson equation, the two-dimensional Poisson equation, in the three regions, region 1, region 2, and region 3 for our Pnpn architectures, and maintaining the potential and electric field continuity at the interface of region 1 and 2, region 2 and 3. The effect of the negative charge possessed by the biomolecules was incorporated by introducing an additional term, NF, at the boundary condition of the SiO2 layer. So this is the SiO2 and silicon channel layer. Here we considered an additional term of NF, which is the charge density associated with it. So I'll not get into the mathematics as it's available in detail in the published work itself, but this is important that the capacitance has to be evaluated in the cavity region as well as in the oxide region itself. And the capacitance of the cavity depends upon the dielectric constant of the biomolecules, and as well as the NF, the charge, is also going to play a role. This is the modeling scheme whereby we first solve the Poisson equation in the three regions to help us to evaluate the surface potential, and which further was used to evaluate the electric field and plot the energy band diagrams. And by introducing the charge effect in terms of localized charges in the model itself, we were able to validate the model results with the simulated ones. So the one on the left hand side, you can see it is the PIN TFET, and the one on the right hand side, it is the PNPN TFET. The curves which are in red, that is in the absence of biomolecules, one can see there is a significantly large tunneling barrier width which is associated with it. And the moment the biomolecules are present, the dielectric constant changes and the tunneling barrier width is reduced. But it seems nearly similar for both the PIN as well as PNP and TFET, but even a small decrease in the tunneling barrier width, as we have already seen, it's going to increase the BT-BT current in the device itself. And that's evident from the IV characteristics of the Mosfet for the PIN as well as for the Pnpn architecture. One can see that in case of the Mosfet, the DMFET, there is hardly any change in the threshold voltage due to the variation of the dielectric constant, as well as a very minuscule change is there in the on current. But if we compare it with the PIN TFET, then although the current levels are extremely low, but there is orders of change in the on current, as well as there is a significant change in the threshold voltage or the onset voltage for this. So by introducing an N-type layer in the PIN architecture, which transforms to PNPN, you can see that there is an orders of change, 5 to 7 orders of change in current, and that is within the detectable range itself. And also it helps in lowering the onset voltage, which is also within the detectable and measurable range itself. The impact of charge was also observed, and we could see that as the charge density was increased, there is a reduction in the onset current as well as the onset voltage increases. And this is prima facie due to widening of the tunneling barrier width, which reduces the current and also increases the onset voltage. And this effect was evident in both the MOSFET as well as the tunnel FET design itself. But there was a major problem. And this we realized when we tried to develop a unified drain current model. The first one being that the source and the drain depletion widths were not accounted for, and that's why there was a need for modifying a modeling scheme. The first step was to introduce the finite source and drain depletion widths in our analytical model. So the Poisson equation has to be solved in 5 regions now, one in source, drain, pocket, channel under the cavity, and channel under the gate region itself. And also the impact of the gate source voltage on the depletion width has to be included. And this will help in developing a continuous expression of drain current, which can subsequently be used in any circuit simulation package also. So we modified and we worked around with the previous model, and we were able to these are the description of the modeling scheme that we modified that model, and we evaluated again the two-dimensional potential and then further the surface potential and the electric field, and then we substituted the expression of electric field, two-dimensional electric field, in order to get the expression of drain current, which is based on the band-to-band tunneling model, non-local model band-to-band tunneling in that. And that gave us fairly good results. As you can see, the proximity of the modeled and the simulated results and the values of the onset voltage of the modeled and the simulated results were very in close proximity. And this is the turning point, I can say, when we try to see that whether this model can be extended for any circuit simulation package or TCAD simulation package in that option. Now, for a fair comparison between a TFET and a MOSFET, it's important to see how much change is there in the drive current with respect to change in the dielectric constant of the cavity region post hybridization of the biomolecules, as well as how it is going to vary with the negative charge which is associated with the biomolecules. So on the left hand side, you can see that there is a orders of change in on current, and it is much larger in comparison to that of a MOSFET. And similarly, there is a significant decrease in on current also as the charges, negative charge associated with the biomolecules is being introduced. A similar effect can be seen in terms of the onset voltage, where there is a significant change in the onset voltage, and it is easily distinguishable in comparison to that of the MOSFET. However, there are certain issues and challenges which we call as the real-time problems, which influences the sensitivity of TFET and FET-based biosensor. And the first one is the partial hybridization of biomolecules, which is caused due to the steric hindrance. And the second is the probe target placement due to the discrete nature of the biomolecules. So this was not taken into consideration previously, and again, for the benefit of non-experts. So this partial hybridization, it's a practical situation where till now we have assumed that the whole cavity was completely filled with biomolecules, but that's not the practical case. And only a part of the cavity gets filled. And even the hybridization of these biomolecules, it actually starts retarding all along the length of the cavity. So you may find a situation where the profile of the cavity once it is partially filled is going to be very different, and I'll be discussing about those cases which we considered as the possible cases due to the steric hindrance. Then the other is the high probe density leads to the low coverage area, and it also hinders the hybridization process. So both of them, they have a significant impact on the sensitivity of the biosensor. So this is the part C. As you can see, this is the case when we consider it to be completely filled, and due to partial hybridization or due to steric hindrance, this could be one of the cases where the hybridization take place at the entry level itself, and the rest of the cavity is empty. Or it can be like a step profile, so it is partially filled cavity region, or it can be like a slant field type profile. So multiple or different profiles were reported uh, in literature, and we try to see whether we can extend the model to take into account to these things. So the major role was that of the capacitance. So the capacitance for a uniformly and fully filled cavity was already developed. So we try to see that if we modeled the partial hybridization case, so we have to find out the effective capacitance in this region, and then again an effective capacitance in this empty region itself. So we developed this expression of the capacitance, and we substituted in our model. Similarly, when we have a non-uniformly partially filled cavity with like a step type profile or a slant profile, then it seems much closer to a case where we have a tapered oxide geometry, and we modified the expression of the effective capacitance of the region and the effective oxide thickness, and that was subsequently introduced into the model. Another interesting case which is possible is that when we are considering a slant field profile, then the slope of this SFP can be different. So the major or I can say the main point of identification whether the TFET is a good choice over a FET-based biosensor is whether the sensitivity of this is really different in both the two cases when we are considering these four different cases. So we carried out an exhaustive TCAD simulation, as well as with the model we checked out that how the IV characteristics changes for these four different cases. And one can see that there is a significant change in the on current as well as in the onset voltage for a TFES-based biosensor for these four different profiles, although the change is hardly 1 nanometer over there itself. And MOSFET-based biosensor was not able to distinguish these four cases in either in terms of the threshold voltage or in the onset voltage itself. So this validates the point that in terms of sensitivity, when we are considering the non-uniform cases, that is a non-uniform the slant profile, where the fill factor is nearly constant, but the sensitivity of the TFET-based biosensor was orders and orders of higher magnitude in comparison to a FET-based biosensor. Now, coming to the most important part, which is related to the placement of the probes or the targets over there. So we took several different cases where the probes, they are placed equidistant, and the one when the gap between the two targets is increased. So we considered a minimum and maximum number of probes which are being used in this analysis, from minimum to 4 to maximum 16 in a cavity length of 100 nanometer each, and the length of that each probe was considered to be 5 nanometer or so. So in all these cases, we realize that the Pnpn dielectric modulated tunnel FET design was giving the sensitivity for this design was 10 to power 3 to 10 power 5 in comparison to a conventional DM FET or even a PIN DMT FET also. The cases which I've highlighted as off, its reason is that the current levels were not significant enough to get into a detectable range itself. So the key advantage is the N-type layer, which has been introduced in the PIN architecture, which has actually helped in improving the drive current as well as improving the sensitivity of the design. But all that, so that is, we are talking about the year 2012 to 2015. The most of the results carried out by our group or by other groups were based on TCAD on mathematical models. The first experimental result, or rather I should say the proof of concept, was reported in 2016 when a silicon nanowire based TFET design was fabricated by applying a novel CMOS compatible anisotropic wet etching approach. And therein, they verified using a CYFRA biomarker, which is for a human lung cancer, and it has proven to be the most sensitive biomarker for the diagnosis of the non-small cell lung cancer. And as one can see on the right-hand side, that even 0.5 femtogram per milliliter, so this much is also detectable for the TFET-based biosensor. So this demonstrates the ultra-high sensitivity of this nanosensor, which is based on TFET design itself. And when we do a comparison between the TFET-based biosensor and the FET-based one, so the FET-based ones, the limit of detection is only in picograms itself. And be it lung cancer, colorectal cancer, ovarian, bladder, everywhere you will see that the range is in picograms itself. Whereas in the case of the TFET, it's in femtogram. So that motivated several research groups to look out for this particular device architecture for verification. And year to 2020, which is the pandemic year when all of us suffered heavily, I figured out one paper has been reported wherein they successfully fabricated this TFET-based biosensor for SARS-CoV-2 detection part itself. And there are certain challenges which are associated with this particular design. The first one being that there is an ion trapping in dielectric membranes which will cause a drift in the characteristics. The second is that although the heterojunction TFET designs have been proposed, but whether a staggered or a broken gap alignment will work out best for the biosensing application. And the last is how the influence of the line edge roughness in the band gap and the transport properties of this, they still haven't been explored yet. But in last 2 years, there have been several designs which have been reported, like the one on the vertically stacked nanosheet gate-all-around FET. This is not for TFET, this is for a FET-based one. And they have reported that the sensitivity for this design is comparable to that of a dual material gate TFET biosensor and much superior than the JL TFET design and the vertical or the traditional Mosfet based biosensor itself. So this is one area where we can explore that how by modifying either the heterojunction design or going in for heterojunction designs like indium arsenide and gallium arsenide based TFET design, or going in for a Schottky barrier TFET design, can we extend this particular concept where the limit of detections can be further reduced and the sensitivity can further be enhanced. So there's a lot, the research field of TFETs has witnessed a rapid expansion the last 5 years or so, and a lot of new materials have come up and a lot of new device concepts have also been proposed. And one expects that these new emerging device architectures will definitely pave way for lowering the LOD limits as well as for improving the sensitivity. So the last 2 slides I'll be dedicating to all the students and the faculty members who have listened to the talk or listened to this concept for the first time. So if you really want to work in this area, there are a few topical reviews which I would like that you should go through. One is by Enuscu in the Nature in the year 2011, and another by David Essini in Semiconductor Science Technology in the year 2017. And there are 2 books which have been written by Mamidala Jagdish Kumar and another by Monsoon Chan. So those of you who are interested, please feel free and go through these books. So to conclude, I've tried to give you a working principle of a TFET-based biosensor under the dry condition itself. Remember, we are not talking about wet conditions, and where the high sensitivity of this design has been discussed. And we have also developed the drain current expression for that. And due to high sensitivity related to this, it's beneficial for detecting even the low concentration itself. The compatibility of TFET with existing CMOS technology and the proof of concept has also been reported in the year 2016, which has going to give a paradigm shift to the point of care applications of this. And for all the young budding uh, members or the faculty members or the students who are interested in carrying out research in this area, I also try to share some of the upcoming TFET architecture designs, which will be definitely useful and beneficial for all of you. Thank you all for your attention. I'll be more than glad to take up any questions.
Okay, thank you very much, Professor Saxena. It was a splendid topic. You talk about the Tunofet, biosensor, biofet was excellent field for us. And first, I would like to, okay, we have a delay between the YouTube and here in our Google Meet. Then I start the question. I have two questions, in fact. First, you show us the approach about biofet using on-state current, right? And some papers, I've read some papers that they are focused on off-state, on ambipolar current. What do you think between these two approaches? Is better to focus on state or better to focus on, or if you have any experience on off-state current?
Yeah, we have also explored this area of biasing the TFET in an off state itself. However, there are two challenges associated with it, and I didn't touch upon those. One is related to the noise. So noise is one of the area which is to be explored, and because the off-state current, the current levels are extremely low, so any kind of noise which is associated with that is going to impact the sensitivity of the device. So if we can somehow touch upon that part, then that the off-state sensitivity part is definitely going to outperform the on-state one itself. So I completely agree. So the work has to be done related to suppression of noise related to that. Yeah.
Great. This was my second question about the noise, but now you
Okay.
already answered it. Thank you.
Okay. Sure.
Thank you.
Sure.
Let me see here in the YouTube. Okay. Another question. You talk about dielectric modulator biofet. What do you think about the charge modulate biofet? Because
if we are going to consider the fixed interface charges at the silicon-silicon interface, that is what we have already taken care of. That is under the dry condition. Under the wet condition, the placement of this charge will not be at the interface, but it will be embedded in the dielectric itself.
right.
And that is something which actually is a statistical way of looking at things. So if we assume that charge, the particle is there in the dielectric itself, then the sensitivity, the way if it is away from the interface itself, we'll find that the detectable range is going to low. But what I assume that the TFET, because it's a junction phenomena, so the sensitivity of TFET will in any case will be better than the FET based or the DM FET design itself. But this is a challenging problem, and wherein the placement and the position and the different cases and the orientation and the distribution of that under the wet condition, that is still to be. I haven't seen many papers related to that part, but that's really a challenging problem itself. Yeah, I agree.
Thank you. I have a question from the YouTube. May you have a look on your chat?
Yeah, sure. Yeah.
From Walter.
So can you comment on the possibilities of selectivity of this type of sensors? Well, I'm not sure what exactly the selectivity of this type of sensors. Maybe if you can.
I don't know. I received from.
Yeah, maybe I think it's partially incomplete, or I'm not able to get this question straight away. Yeah. But as far as the opportunities in terms of the sensitivity is concerned, yes, I can see that if we extend the same concept on heterojunction defects,
All right.
That is one way going ahead for that part. Yeah.
Okay. Okay, I think that's fine for us. Thank you very much for your presentation. Thank you for coming to accept to be here with us with our mini colloquium. Let's move to the next presentation. Thank you
very much. Thank you.
Thank you. Okay, let's again share my screen. Okay. Oh, let's move to the third one. Okay. Let me just we are here in IEEE EDS Brasil chapter mini colloquium. We already have two presentations that started third one. The third one, the title is Trends and Challenges in Nanoelectronics for the Next Decade. And this talk will be presented by Professor Elena Irani from University of Bologna. She received the PhD degree from University of Bologna, Italy. She is currently associate professor at the University of Bologna. Her research interests included the development of physical transport model in semiconductor device and numerical analysis techniques, with special emphasis on the study of a quantum-confined device, such as FinFET, silicon nanoart, steep slope device, as well as quasi-ballistic transport in nano Mosfet. He is author and co-author of more than 108 papers published in referred international journals and in proceedings of major international conferences. He is presently an IEEE senior member, Electronic Device Society Distinguished Lecturer, member of the Technology Computer and Design Committee, and served as associate editor of IEEE Transactional Electronics. And thank you for accepting the presentation. Welcome, Professor Elena, please.
Hi. Hi. Thank you very much for the invitation. So I try to share my screen.
Okay, I stop mine.
Okay. Just.
Great. You can see your screen. Great.
Okay. Just one moment. Do you see the presentation now in presentation mode? Okay.
Perfect.
So thank you for the kind invitation. As already anticipated, my talk will be on trends and challenges in nanoelectronics for the next decade. Obviously, the argument is really very wide, and I will try to give an highlight of all the devices that are now under investigation for future electronics. So that is the outline. I will start with a brief recap of the Moore's law that probably we all know. I will discuss a bit on the improvement that were given by scaling of devices. I will focus on the power issue that now is the key performance metric for new technologies. and I will give an highlight of what are called the beyond the Cmos devices that are now under investigation. I will give also a benchmark between these, I would say, exotic devices. And finally, I will conclude with some prospects and challenges of all these devices. So if we discuss of nanoelectronics, we have for sure to start from the Moore's law. That is a well-known law that said that that Moore give a forecast saying that there would be a doubling of the number of transistors per chip every 2 years. This would give a lower cost per transistor. This law was published by Moore in 1970, but if we come back and if we look to the technology improvements that we had in the last 120 years, we can see that we started our computation, I would say, with electromechanical devices, and this graph showed the calculation per second for a fixed cost. And you see that we had in this 120 years, we had an exponential improvement of the performance of our circuits. So we move from electromechanical devices where we were not able to reach one operation in 1 second. You see, it's here we have a number lower than 1, and we moving from mechanical devices to the invention of transistor and then from integrated circuits. We can say that integrated circuits came to the forefront. And there is an extrapolation that eventually computing devices can achieve intelligence of comparable to human brain, perhaps in this an extrapolation in 10 or 20 years. So just a recap of scaling. The scaling rules were published by Bob Denard. It's a very famous paper, and the basic idea of scaling is to adjust the dimensions and voltages in order to keep the same electrostatic behavior of the device. And in principle, if you look to the performance metrics like the current, how scales the current, the area, the power, the good news is that if you would be able to scale the device, you could achieve a better delay, so you could improve the performance at a fixed power density. So these are for sure good news. So the scaling, in principle, improves performance. So the scaling improves performance, but also widens the market of electronic devices, because as probably already knows, have experienced in his life, we had a widening of the electronic devices that now are, I would say, everywhere. So now electronics has become to be an habilitating technology. So we move from analog RF applications to artificial intelligence, power devices, for example, the powering of electrical engines, obviously sensors for IoT, and also biochips application to bioelectronics. So now we have really a huge market for electronic devices. Now I want to focus a bit on the performance improvement that in principle we should achieve with scaling. I put here a question mark. We will discuss, because we will discuss and we will see if we really have a performance improvement. So what are the scaling roadblocks? In the last 10 years, perhaps 15 years, we experienced that it was difficult to scale the oxide thickness, for example, because if you scale the oxide thickness, you exponentially improve the gate leakage. To solve this problem, this roadblock, engineers were able to introduce a technology breakthrough using high-K dielectrics instead of silicon dioxide and the metal gate. We experience also a different scaling of the channel length and the oxide thickness that led to what are called short channel effects. That means the degradation of the performance and increase of the leakage current. And to solve this problem, again, we moved from planar devices to three-dimensional devices like FinFETs. So that is, these are new device architectures. And we moved also to high mobility channel materials in order to improve the on performance. Again, to improve the on current without shifting too much the voltage, the threshold voltage, we introduced strain in the channel, and again, high mobility materials would improve the on current. Finally, if we move to small sizes, that is obviously the target of scaling, we need to take into account that we have more parasitics, we have an increase of variability, so we have a larger statistical variation related to the process fabrication. We need to take into account quantum effects. One moment, I would get the laser. Okay, we need to take into account quantum effects that take place at very small sizes, and also now we have devices so small that we need to model each single atom to get the electronic properties, the correct electronic properties of such devices. So now we can say that scaling requires really continual innovation in transistor structure, but not only, also on materials. These are the projected scaling according to IEEE of the sizes. For example, in green, you see the channel length, and you see that the scale, the projected scaling showed that the scaling of the channel would stop almost in 2028 and remain constant at 12 nanometers. So because we are reaching really the physical limit of our materials. And also because we have the problem related to the power dissipation. In fact, if you look also to the CPU throughput, you see that if we project the CPU throughput at a constant power density, so keeping constant the power density, we need to fix or to stop the increasing of the throughput in order to keep the heat at a reasonable value. In fact, if you look to the CPU throughput at maximum frequencies, in principle, it would increase again exponentially. So now we can say that the thermal constraints that are caused by the power density means that we need to throttle CPU more frequently to maintain the same power density. So we can say that now the scaling paradigm is to focus on, first of all, on power, then on performance, on the area, and on the cost. This scaling paradigm is called PPAC and is currently the current paradigm. So now we are here with FinFET. We are moving to nanosheets that are here. So we use a three-dimensional devices, nanosheets or gate-all-around, lateral gate-all-around devices. So the prospects are to move to vertical devices. For example, with the memory, we already use vertical devices, and even to take advantage of the three-dimensional of the vertical dimension to stack devices, various devices, one over the other, in order to get better performance, so higher throughput, computational or say computational performance using the same area. So now we are at this point. So you see the major breakthrough that we had in the last 20 years. So this was the introduction of copper for the interconnect. You see that here we see also the gate length scaling. We see that around 2000, the gate length scaling reduced its slope. So we took advantage of strain to improve the performance. We introduced metal gate IK dielectric to reduce the leakage. We moved to three-dimensional devices with FinFET in order again to get to reduce short channel effects. And now, perhaps in a few years, we will see the introduction of nanosheets in the market. So we can say that we had three different ages of scaling. So we moved from the classical geometrical scaling that was given by the Denard rules. Now we are in the area that we can say the equivalent scaling, where means that we reduce the horizontal dimension in conjunction with the introduction of new materials and new physical effects, and we take advantage of the vertical dimension. Perhaps from now on, we will have a 3D power scaling. So we will see a transition to complete vertical device structures with heterogeneous integration in conjunction with reduced power consumption. With reduced power consumption. So the power issue. Now we see that power is a key word in this talk, because we can say that now we live under the power tyranny, because if you look to this very famous plot that shows the power density as a function of the scaling of the channel length, in principle the active power should remain constant, more or less, but you see that we have really a huge exponential increase of the leakage power if we scale the gate length. Now here we have we are almost in this region, I would say, where the leakage power in principle is larger than the active power. Remember that the active power is, I would say, a good power that is used to make the computation, whereas the leakage power is really power that we dissipate for doing nothing. So the leakage power is given by many contributions. In principle, we have the gate leakage that now is not very important. We have the junction leakage given by the reverse junction, but and we have the major contribution, that is the off current that we have between the source and the drain when the device should be in principle in the off state. So now the scaling focus on the reduction of this leakage current. Just a recap, that is the turn-on curve of a Mosfet. You see that we have, that is the on current, the off current, in order to get, so the active power is proportional to VDD square. So if we want to reduce the active power, we need to scale VDD. However, if we want to keep the performance, to get the same performance, we need to scale not only the VDD, but also to scale the threshold in order to get the same gate voltage overdrive, okay? So this window, in order to get the same ion, that means performance. But if you see that if we shift this curve towards the left, what we have is that so if we reduce the supply voltage, we have an exponential increase of the leakage power, of the leakage current. So in principle, it would be the target, the purpose would be to get the same on current keeping the same leakage current that we have for a larger supply voltage. You see that means that we could get a steeper slope. We can achieve this with a device with a slope that is steeper than the one given by the conventional Mosfet device. We will go a bit into the details of this discussion later. So now if we look, if we plot the total energy of a device, the total energy is given by the sum of the dynamic energy. As we have seen that the dynamic energy is proportional to the square of the supply voltage. So we get this green curve. So we increase the energy, the dissipated energy, increasing the supply voltage. On the contrary, we have seen that if we scale, we have previously seen that if we reduce the supply voltage, we increase the leakage. So the leakage energy is given by this orange curve. The sum of these two contributions is the red one. So you see that there is a minimum. So you don't do a minimum of the energy that you get and the minimum of the supply voltage. So it does not make any sense to scale the supply voltage lower to this VDD mean, because at this point you get a larger energy dissipation. In principle, if we would be able to get a device with a lower leakage, so if we would be able to move from this dashed orange curve to this one, that means a lower leakage for the same VDD, we could get this red curve. So we could be able to get a lower energy for a lower supply voltage. So in principle, that is why for 10 years we are investigating for more perhaps than 10 years, we are trying to find devices able to give us a slope lower than the classical 60 millivolt per decade value that we get with conventional devices. So the devices that have been proposed to solve this problem are called beyond CMOS devices. So in general, beyond CMOS refers to potential future digital logic technologies that expand beyond the present CMOS scaling limit. That means that in principle, we could extend the circuit technology to fundamentally new approaches, so also to new computing paradigms. Beyond CMOS is what is called beyond CMOS is based on 3 different pillars. So we have beyond CMOS devices for memory applications. There is a huge research on new memory computing devices, new memory devices, also for computing. So there is really a lot of research on new memory concepts. Then we have obviously devices for logic, that is the one where I will focus on. And also we have beyond CMOS related to architecture. So that means inventing a new information processing platform technology in order to get new domains of functionalities and applications. So focusing on devices, just a recap that sometimes we forget that what is a device? A device is a structure that provides the physical means for representing, but not also representing, and manipulating a computational state variable. Perhaps usually between 2 states that are the 1 and the 0 and the 1 bit. So you need to represent and manipulate a computational state variable. So the computational state variable, so the taxonomy of emerging devices is shown in this graph. So we have the computational state variable that can be related to charge. In conventional Mosfet, we have charge flowing throughout the channel of the device. But we have also, we will see that there are ideas to use different state variables that are not related to charge. Then we define we can define the devices also according to the structure or the materials that we use for its realization. So we can use conventional materials and structure, but also novel materials and novel device structures. So here you see that this taxonomy splits the space in, I would say, 3 regions, because you see we cannot have a conventional device that does not take advantage of the charge to compute the bit. So we here in the orange, in this orange rectangle, we will see we have the devices that are extending the conventional Mosfet to the end of the roadmap. In this green rectangle, we put, I would say, the non-conventional FETs and other that are charge-based, where the information is again charge-based, but we have also alternative information processing devices that we will see mainly are related to are given by spin devices and magneto devices. So if we look, if we put devices in this graph, in this schema, we will see that here conventional, I would say conventional end to the roadmap devices, we have horizontal gate-all-around, FinFET, vertical gate-all-around, CNT FETs that are almost, I would say, conventional devices. Then we have what are called novel devices, where the transport mechanism is not the classical thermogenic emission over the barrier. Here we have the tunnel FET, the nano-electromechanical devices, negative capacitance FETs, the MOT FET, and other more exotic, I would say, devices. And finally, you see that in novel devices with non-charge state variable, we have mainly devices where the information is given by the spin of the charge or the magnetic field, or we have finally quantum bits. Okay, just a recap. In order to realize, if you need to realize digital circuits, so you need to have a computation. You do not need only to have a good device. So there are requirements that must be satisfied by each device in order to be used to realize computation. So there are logic requirements. So you need nonlinear characteristics in order. That means also a large gain in order to get good noise margins and a good signal to noise ratio. You need to prevent feedback. You do not want the output to affect the input of your gate. You need to be able to realize a complete set of Boolean operators, such as, for example, not, and, or equivalent. And you need also, very important, to concatenate various operators in order to get your final calculation. There are also physical requirements. In principle, the device should be scalable, otherwise nobody will take into account this device, should be fast, and should be also not power hungry, absolutely not power hungry. There are also technological requirements. In principle, it would be a good news if this device could operate at room temperature or even higher. Should have a low sensitivity to technological fluctuations, so to fabrication variation. Should be reliable. It should be in principle compatible with standard CMOS in order to take advantage of interface and connection schemes of CMOS devices. Should be also not only architectural compatible, but also process compatible in order to be fabricated on the same wafer. And in principle, you should it should have low parasitics. So you see that a solid state device needs to satisfy all these requirements before it can be considered as a good candidate for an element of an integrated logic circuit. So there are a lot of requirements that must be satisfied. The good news is that emerging devices offers also fundamentally different and in some cases unique characteristics. For example, these devices here that are related to magnetic fields or also spin have a memory capacity. So with this, you can take advantage of this feature in order to realize novel and non-traditional circuit concepts in order to be able to achieve their full potential. Just to see some example of what are the computational variables. For example, in standard devices, we have the charge. That means that we have a current, a voltage, and the charge. For example, in ferroelectric devices, we take advantage of electric dipole. So we have a polarization of a polarization field, and we take advantage of the fact that polarization can be up or down to store the information. We can take advantage of a magnetic dipole as a computational variable in spin or magnetic-based devices, or we can have also position as a computational variable. We will see in nanoelectromechanical devices. So a final remark is that in order to get a concatenation of our gates, we need to take into account that the output of a device needs to be the same computational variable as the input of the next gate. Otherwise, we need a transducer, and this happens, for example, with spin-based or magnetic-based devices, where, for example, you need to use the current to create a spin torque, so to move the spin from up to down. You need the current, and then you need the transducer to transduce this spin to again a current. Or, for example, with magnetic-based devices that are voltage-driven, again, you need the voltage, you need the transducer to transform this voltage in a magnetic field, and again, another transducer to switch from magnetic field to the voltage. That means that in the realization of your function, you need to take into account that you need also these gray gates, these gray structures. Okay, now just a brief discussion of the problem of the slope to see why, to understand why the emerging beyond Cmos devices can improve with respect to the conventional Mosfet. So in the conventional Mosfet, the current is the transport mechanism is what is called the Thermogenic Emission over the barrier. That means that only carriers with an energy higher than the barrier can move from the source to the drain. That is the potential barrier that we have, the energy potential barrier that we have within our channel. So if we increase the gate voltage, we reduce the barrier, as is shown here. If we reduce the barrier, we increase exponentially the number of carriers that can flow from the source to the drain, and we have this exponential increase. That is the slope. So the slope is the inverse of the derivative of the current as a function of the voltage. So that is this function here. This derivative can be split in two terms, so we can make the derivative of, let's see in the inverse form, the derivative of the surface potential with respect to the gate voltage. That means how our gate voltage is able to modify this potential barrier. And then we have the derivative of the current as a function of the variation of this surface potential. This contribution is called body factor. And this one is related to the physical conduction mechanism that we have in the channel. So how much the current increases as a function of this variation of this energy potential barrier. The first term is given, so the variation of the surface potential as a function of the gate voltage is related to the paraelectric capacitance voltage divider that is called body factor. And then we have this derivative that is theoretically for ideal devices for thermogenic emission over the barrier gives the famous 60 millivolt per decade value. So in order to improve this slope, so the best of conventional devices gives 1 for this term and 60 millivolt per decade for this term. So in order to break the 60 millivolt per decade wall, what we can do? We can reduce this contribution to a value lower than 1. That are the devices that are called that are where the transport mechanism has a positive feedback inside. And this term, we can reduce this term in which way? Not using thermogenic emission over the barrier, but modifying the carrier injection mechanism in the channel. So I will show now, I give a brief highlight of the most famous devices that have been proposed in the literature. For example, the Mosfet is a device where we try to modify the transport mechanism, because instead of having the carrier thermogenic emission over the barrier, we are relying on a tunneling of carriers. So the tunnel fit, perhaps all of us, we all know the tunnel fit is a PIN device. So the energy potential profile is this one, that is the P region, where we have a lot of holes. You see the energy, the Fermi level is almost in the valence band. We have an intrinsic region where in equilibrium the energy, the Fermi level is in the mid gap. And finally, we have the N region where the Fermi level is almost close to the conduction band. So that is the band profile in the off state. You see that carriers entering the source experience the band gap, so they cannot flow from the source to the drain. Whereas if you increase the gate voltage, you push down the energy barrier, the energy bands in the channel. So you push down the energy bands, and you see that now the energy gap thickness is very, very small, is very thin, and so we can have what is called the tunneling mechanism, the band-to-band tunneling from the valence band to the conduction band. So now the transport is no more thermogenic emission over a barrier, but is a tunneling throughout a barrier. Theoretically, you could get very good results. There is really the advantages are that you could, in principle, get very steep slopes, high on-state current higher than Cmos at very small VDD. The current, in principle, should not depend on the channel length, because the tunneling mechanism does not depend on the length of the device, but only on this region. So this could be as long as you want, in principle. And in principle, also, the current should be independent on temperature. There is really a huge investigation on such device. I will go on just to show you that there are, I would say, tens of devices that have been proposed in the literature, probably hundreds. Just a very famous sketch that shows that these are simulations of various devices, tunnel FETs. It is a very famous paper by Alan Sebo. You see that is with the dashed curves, you see the conventional CMOS at 2 VDS. So in principle, from simulation, taking advantage of heterostructures and various tricks, you could in principle get very good slopes. You see very steep slopes. That is from the theoretical point of view. But if you move to experiments, you see that you do not see very good results. I would say not good news, not very good news. You see that the curves are almost flat, because there are many technological challenges that must be still faced. I have no time to go into the details, but there is really a lot of work in order to improve this kind of device from the technological point of view. Devices, instead, there are devices where you take advantage of what is called the positive feedback. For example, I will give only a very brief highlight of them. This is a very interesting device, that is the Mosfet, nano-electromechanical FET. The idea is shown here. You have a cantilever that is your source contact, you have the drain, and you have a gate contact that is here an actuation electrode. So in principle, if the voltage here is low, you do not have the connection between the source and the drain, so the current is in principle zero, in theoretical zero, negligible. Whereas if you apply a voltage in the electrode, in the actuation electrode, you can pull down the source cantilever in order to get the switching between the source and the drain. You see that is measurements, so experimental results. You see here the photo, very nice photo. You see that if you increase the voltage to, it's about 1 volt, you get really a steep increase from negligible current to large values of the current. So in principle, you could achieve a slope almost equal to zero. Unfortunately, there are problems related to that. You need a not so small voltage in order to pull down the cantilever. Then there are stitching problems related to the fact that you have problems in again pulling up the cantilever, and you have also hysteresis. So if you want to pull up the cantilever, you need to use a voltage that is different to the one that you need to pull down the cantilever. So there are problems related to the reliability, because you have something that is moving up and down. So the switching times is slow, because you need time to pull up and pull down this cantilever, and also the size is not so small. So I would say that it's unlikely to replace CMOS. Now it's explored as a components for more for memory or sensing applications. Very famous negative capacitance for electric felt that was proposed by Salahuddin almost more than 10 years ago. So the idea is to take advantage, to modify the coefficient 1 plus the device capacitance over the oxide capacitance, in order using that in principle should be 1 or larger than 1, using a different oxide with a negative capacitance. If you see of the ferroelectric, the capacitance of the ferroelectric is negative, you see that you get 1 minus something. So you can reduce the capacitance voltage divider to a value that is between 0 and 1. It must be larger than 0, otherwise all the structure is unstable. Again, there is really a lot of investigation, a lot of research on such device. The slope, these are again experimental devices. Now the oxide that is used for negative capacitance devices is usually hafnium dioxide, because the good news is that it's compatible with CMOS technology. it gives a slope that is lower than 0. However, again, we have the problem of an hysteretic behavior. It's very difficult to design such kind of device because this negative capacitance, you can get a negative capacitance only if the thickness of this insulator is in a very tight range. So you need to be able to control tightly the thickness of your oxide, and also the switching of this of the polarization field is slow. So usually these devices are slow, show long switching times. Finally, what is called, sometimes known as the Mosfet. The Mosfet takes advantage of a sharp change in resistivity of an insulator to metal material. An insulator to metal material is a material that changes its resistivity almost between an very large resistivity, that means insulating behavior, to a very small resistance, that means a metal behavior. So you put in series to the source of your device such kind of material. So the idea is that if this material is in its insulating state, you measure a very low current, whereas if you are able to switch the state of this material to a low resistive resistance state, you get a huge reduction of the resistance. That means a huge improvement in the current, a huge increase of the current. The problem is that you need relatively large voltages, as you see, to switch the properties of this material that are not compatible with the target of low supply voltage application. And there is also hysteresis that can be limited, I would say. Finally, we can move briefly to non-conventional devices that are almost spin-based. Again, the most famous device is what is called the SpinFET. All these devices, I would say there are only a few prototypes, so the investigation is almost is more or less a theoretical investigation. So the idea here is to use a ferromagnetic material in the source with a fixed polarization. Then you have again a ferromagnetic material in the drain, but with a free polarization. And we have a tunneling magnetic resistance that is given by the structure. So you have again a fixed ferromagnetic material. The idea is that you inject a current with a specific spin equal to the one fixed in the source. The gate is able to switch the spin from up to down. So if you get you measure the spin in the drain. So if the spin is parallel, if the spin in the drain is parallel to the one in the tunneling magnetoresistance structure, you have a small resistance. So if you get a parallel spin as shown here, you have a small resistance, so a large current, whereas if you get here a spin that is anti-parallel to this fixed one, you have a large resistance. So the idea is that it offers the capability for non-volatile information storage, because here the spin is memorized, so you can measure after some time the same spin, so you get the same information. The read and write operation have not yet been fully experimentally verified, and the major problem is that the difference between the parallel and anti-parallel configuration, so the variation in the resistance, is very small at room temperature, so very difficult to measure. Then we have the devices that are called nanomagnets, so where the information is a magnetic field. For example, that is a majority gate realized with nanomagnets. So you have usually these devices are chains of nanomagnets, like the one shown here. They are similar to domino, to the domino game, I would say. So the binary information is represented via the magnetic state. So the field, magnetic field is up or down, and in principle, you take advantage of the fringing field to get the interaction between this magnetic island. So the dipole interaction between these magnets flip the magnetization of the output, for example. That is a majority gate that sense the number of gates where for example, here the spin is the magnetic field is up or down. So you need to prepare all the magnets is in a quasi-stable equilibrium state. So the input state of the magnets causes the magnets to choose one of the two stable equilibrium states. It's relatively fast. This kind of devices are relatively fast because you start from an unstable state. But the dipole interaction that switches the magnetic field is very sensitive to the shape of these magnetic devices. Finally, I would say last but not least, we have the qubits that are now proposed to make quantum computing, quantum-based calculations. So you know that in quantum computing, you take advantage of the fact that your wave function is not or 0 or 1, is not that are the classical bits, but is a superposition of the two states. So you have that your states is not only 1 or only 0, but is the superposition at every time of these two states. So in principle, you can, this gives a very, the fact that you can perform parallel computation on a massive scale. So you can take advantage of parallel computation because you have this superposition, and you can, it has been demonstrated that you have what is called the quantum computing supremacy on some topics that are molecular modeling, image recognition, cryptography and communication. Unfortunately, you have a huge power dissipation of all, not of the qubit, but of all the quantum processor, because you need to keep all the structure at a cryogenic temperature. That means a huge power dissipation. And the major problem, that is one problem, and another major problem is what is called the coherence. That means that after some time you lose this superposition of the two states that affects also the fidelity of your quantum bit. That means that you need, if you have a low decoherence time, you need many physical qubits to realize one single ideal qubit. There are many, I would say, technologies that have been proposed to realize the qubit. The most famous is a superconducting qubit. Now they've been shown in the literature. The largest is with 128 qubit processor, but there are also other technology platforms that have been proposed. For example, semiconductor-based spin qubit. That the main advantage is that it could be realized using the silicon technology, the well-known silicon technology. So briefly, the benchmark. Only a few highlights of the benchmark between these devices. That is the energy versus delay. The green dots here, you have the value that you get with high performance CMOS, and this one is the low voltage CMOS values that are from IRDS. The benchmark has been done considering 32-bit ALU. And you see that spintronic devices that are current driven and voltage driven are slower than CMOS, show a slower, and the silicon spin-based devices also experience a larger energy, because you need energy to switch, huge energy to switch the spin. Whereas the tunnel FETs that are given by tunnel FETs devices that are given by the red dots, you see that can improve. They have the delay that is comparable to between high performance and low voltage devices, but with the lower energy. So these results are almost quite good results. We can plot also the power density as a function of the throughput. So in principle, the preferred corner would be here, high throughput with the low power. With the one constraint, there is one constraint in this plot, that the power densities, there is a limit to the power density of 10 volt over centimeter square. So you see that all these devices reach the limit, so they stop here. That means that they stop to the power density that is the maximum. So the CMOS cannot achieve its maximum throughput because we have this limit. You see that we have that spin-based devices again reach the power limit, whereas magnetic devices that are almost here have a throughput that is not bad, comparable to low voltage CMOS, but with a comparable power density. Also, the tunnel FETs that are almost here are similar to low voltage CMOS. Finally, that is an interesting benchmark that is on the capability of drive interconnects. So that the idea is that we plot the delay and then the energy versus delay, or you see the delay versus energy of passing data through a 10 micron lens interconnect. Here dynamic energy becomes more important because you have to charge and discharge the capacitance of this interconnect. What we see is that is a zoom. That means that these light blue are all I would say spin or magnetic based devices, and you see that spintronic devices are much slower compared to charge-based devices that are this one. And then I've done a zoom here where we plot also the other charge-based devices. So if you have to drive, the conclusion is that if you have to drive an interconnect, non-conventional devices that take advantage of non-charge-based information are much slower than charge-based devices. And note that this gap between the charge and spin-based devices is larger considering the interconnects with respect to what we got for the full adder. Okay, I will skip this one. Prospect and I will give all the information are taken from this paper. That is a very nice paper. I suggest you to read this one. That gives a lot of hints on these new devices. So prospect and challenges, that is the conclusion. So we have seen that we are facing many challenges related mainly to the power dissipation and the energy efficiency of our devices. In order to be able to use low supply voltage electronics, we need to invent new devices with new physical mechanism or structures. What are called beyond CMOS devices are based on various computational variables. So in principle, we need to perform a transduction between current, voltage, spin, magnetic fields, and stuff like this. And for sure, we need additional fabrication improvements for all the devices that we have seen that are really at their very, very early stage of realization. We can say that for charge-based devices, the most promising seems to be the tunnel FET. There are various realizations, but seems to be the leading option. Whereas for spintronic devices, we can say that they have a longer switching delay because they are limited by the ferromagnet switching speed. But there is a good news that there are advantages related to non-volatility and reconfigurability of these devices. That means that we could take advantage of these properties to realize new types of circuits or new types of computing paradigms. Last, that is my personal feeling, is that a beyond CMOS device competitive against CMOS has not been identified yet. But the idea now is to realize hybrid systems. That means to create new technologies that can complement CMOS rather than completely replace CMOS. The idea is the idea of that is to realize hybrid system that could improve the system performance, not the single device performance, but the overall system performance. So there is a lot of room for improvement. That means that there is a lot of work to do. That is a good news for young students or young researchers, because that means that there is really a huge variety of fields where you can give your valuable contribution. And with that, I have finished my presentation. Okay.
Excellent. Thank you very much, Elena. Very interesting talk. And
Thanks.
now, just 1 minute, because there are a delay between YouTube and here. But I will start.
Okay.
The question.
Okay.
Let me ask you: what do you think about reconfigurable FETs? Do you think it's a possibility? Or...
Okay. So I would say that I know that there is a lot of work on reconfigurable FETs that are devices, just for the one that does not know such kind of devices, that devices where you take advantage of Schottky contacts in order to use a single device like a NMOS or a PMOS. The idea is that in principle, you could realize circuits with a lower number of transistors. The problem is that you need additional gates on your structure. So my feeling is that if you stay on lateral devices that are they will never have a future, because they are large devices, long devices. You cannot scale because you need to have also the spacing, enough spacing between the contacts. Whereas if you would be able to move to vertical nanowires, for example, in principle, you do not have anymore such kind of problem because you take advantage of the length of the vertical dimension. I would say that I have not cited here in these devices because they are more advanced, I would say, than beyond CMOS devices that are at the front end. They are more close to not for sure to fabrication, that because there are many experimental realization of such devices, but more similar, I would say, to conventional nanowires.
Okay, thank you very much. In the chat, we have some questions from the YouTube. If you please have a look.
Can comment on the possibility of selectivity.
No,
that is the one. Can the non-charge device compete with the charge devices for power applications? You mean power? You mean power application like GaN, silicon carbide? So to realize power devices like LDMOS or
probably
or stuff like this. This I think that that is not the target, because for power application, for sure, you need devices that can drive a relatively large current. Spin-based devices cannot drive a large current. So no, no. The answer is almost no. I'm not completely sure. I would say 100%, but my feeling is that they will never compete, because there is not the purpose. They were not thought for power application.
okay.
Is there another device other than TFET that present a low slope due to its conduction mechanism, or other devices with small? Yeah, there is the one that is called cold source device, where you put a filter between the actual source contact and the channel. This filter that is almost a junction, I would say, or there are various approaches. The idea is that you filter out with this structure, specific structure, you filter out high energy tails of the Fermi statistics. That means that you filter some part of the charge that flows over the barrier. There are some realizations that gives very poor results. A lot of simulations that in principle show relatively good results, but I think that they still have more or less the same problems related to tunnel FETs, because if you have traps at the junction on the cold source, again you smear out the good slope, and I would say that the tunnel FETs up to now are still the best devices that have been proposed in the literature up to now.
Thank you. The last one.
Yeah, for those devices that use variables other than charge, current, or voltage for computation, wouldn't the transducer induce additional limit? Oh, for sure, yes. That could outshine. Yes, I didn't discuss that, but for sure, yes. The conversion the transducers are an important aspect of such devices.
Okay, thank you very much, Elena.
Thank you.
To see you again after 1 week, 1 month ago. You are in Udine, in Italy.
Yeah.
A conference. Now we are here in a distinguished lecture presentation. Thank you very much for your presentation.
Thank you for the invitation.
Okay, let's go to the next now. Just a minute here. Okay. No. Okay. Just a minute to show the last. Okay. Well, now let's go to the final presentation of this mini colloquium. We are here now in 11 in Brazil. We are people from many places of the world. Professor Hiroshi from Japan, Taiwan, Japan. Manu Saxena, India. Elena from Italy. And now Professor Corlais from Belgium. Then the title of the presentation is Past, Present, and Future of Microelectronics. 75 years of material and device challenges. The paper will be given by Professor Barclays. He received the PhD degree from KU Leuven, Belgium. He's professor at KU Leuven, Belgium since 1990. He was with IMEC Leuven, Belgium from 1984 till 2016. His main interests are semiconductor technology, device physics, low-frequency noise phenomena, radiation effects, and effects engineering. He co-edited 6 books, co-authored 16 book chapters, over 1,200 conference papers, more than 1,300 technical papers. He is editor, co-editor of 70 conference proceedings. He is a fellow of IEEE. He was a chair of IEEE Benelux section, elect board of government member, and elect Device Society vice president for chapters and regions. He was EDS president 2008-2009 and division director IEEE board of director. He is a recipient of IEEE Third Millennium Medal and received the IEEE EDS. Thank you very much, Professor Barclays, for accepting to be here, and you have the audience for you.
Okay, I will try to share my presentation.
I will stop mine.
You have to stop yours, yes.
Okay.
No,
Not yet.
do you see it?
No.
No.
Again.
Yeah, I don't know why it's not working.
You have to select full screen and then click in the full screen in the window.
Yeah, that's what I'm trying to do, but nothing is happening.
After selecting screen, you have another window. You have to push in the full screen again and then share.
No. There seems to be a problem.
Yes. If you want, okay.
Nothing is happening.
Okay. Let me try again. Let me call a friend here. And Fabio, any suggestions? Is our TI people here? Not. Okay, Professor. Two things. If you want, you can send me your presentation. I can pass. You can talk. Otherwise, you can try again if you want.
Okay, I will try again. Moment, I save it. No, nothing is happening.
You are using only one screen or 2 screens?
I'm using one screen.
Only one screen. Okay.
Yeah, I removed the other one. Only one screen. That was a problem the previous time.
Strange. Okay, no problem. Is large presentation you can send me?
Yes,
Okay.
I cannot send it by mail.
Okay.
Yes.
Let's try one. Thank you, Sachena. Thank you very much for your help.
No problem.
Okay, I apologize for the difficulties. I'm an honor to be invited. Of course, I was a little bit nervous, knowing that there are three same topic. So I say, okay, what will be the problem with overlap? And I say, well, okay, maybe overlap, I can avoid that by deleting slides while the other people are speaking and hoping that there are still some slides left at the end. And lucky, yes, I have slides left over. But then I became a little bit nervous again after listening that the human brain is becoming tired of being focused on one topic. And now most of the people are already listening for 3 hours. So I have to do my best to keep your presentation. So I want to speak about the evolution of microelectronics. Electronics with the evolution of the human being, where that, as you can see on the slide, first of all, there was an interest in bananas, and nowadays there is only interest in sharing microelectronic devices like smartphones and things like that. In order to be able to share a smartphone, we are relying on the invention of the transistor, which was, as we have heard already earlier this morning, in 1947. There we had the first transistor. In 1958, we had the first IC by Jack Kilby, but only in 1961, we could speak about the first monolithic IC by Noyce. And in 2008, sorry, I have to go out because I got a wrong presentation. One moment, please. I noticed I got an older version, so I will switch immediately. Yes. Okay. And nowadays, in 2021, IBM has been reporting on a work together with Samsung that they are doing 2 nanometer nanosheets. So that means this year we are indeed celebrating 75 years of microelectronics. If you look over the history, and I'm not going to do that because Professor Iwai gave an excellent overview, then we see that the beginning of the 1900s, where the vacuum tube, we had to wait till 1947 for the first transistor. And nowadays, we are already entering the deep nanometer area, devices below slide. We are now able to come up with a very high packing density. But that's not the only challenge. We want to increase the packing density for 2 reasons. And that is we want to increase the performance, and at the same time, we want to reduce the cost. And you see that by entering the 2, 3, and 1 nanometer area, we are also entering the dimension of the bacteria. Moore's law is dealing with 2 important parameters, the density and the cost. That means the number of transistors per square millimeter should be increasing when we are scaling down. And at the same time, the cost of the devices should be lower. But we have to take into account that fabrication of smaller technology nodes are becoming more and more expensive. Where for a 130 nanometer node, you needed about 1.5 billion to build a fab. For a 7 nanometer node, you need about $8 billion to build a fab. So the cost of building the fabrication sites, that if we do high manufacturing, high volume production, and at the same time, we have to take into account that the design cost is also increasing because the circuits are becoming much more complex. But finally, what we want is that the cost per transistor is going down. That's the end goal. increasing performance, increasing packing density, lower cost per transistor. And if you look around what's happening, a lot of new 300 millimeter fabs are being on the drawing table today. Intel, for instance, is opening a 10 nanometer fab in the near future with an investment of $8 billion. TI is thinking about building 4 new fabs with a total value of $30 billion. In Europe, we have Bosch building a new 300 millimeter fab. And Intel is also planning to open a new facility, 2 fabs in Germany, total investment of $80 billion, and they are relying them with about 6.8 billion euros. At the same time, there are a lot of rumors, noise that Global Foundries and ST Microelectronics in France were fully depleted SOI, and Japan is closely collaborating with the US to open a new facility in 2025. So see, a lot of new fabs are being under construction. And that you can see here on the left part of this view graph, where you see the number of 300 millimeter fabs over the years. And you see that this year, already 10 new fabs should open, as indicated at the bottom part of the view graph, where you see the 10 different fabs that should start this year. And if you look at 2023-24, more and more fabs will be constructed. And by 2026, there will be more than 200, 300 millimeter fabs around. So that means that microelectronics is becoming a very, very important factor in our business. And you can see that here, if you look at the industry, $50 and $100 billion. IC fabrication can go up to electronic systems, and then a huge amount will go to software and handling of big data. In 2021, about $560 million was the revenue of semiconductors, which means an increase of about 26% compared to 2021. And then we have to keep in mind that 2020 and 2021 are 2 years where we had problems with the pandemic. Due to COVID, there was a shortage in the delivery of the components. So that means due to the delivery, due to the problems with the materials, all the fabs were not running at full capacity. Otherwise, that figure of $560 billion would be much, much higher. So that means there's a lot of fab spending going around. And if you look at the predictions, and we always have to be careful with predictions and the numbers, but at least they are giving a very good, clear trend. Then we see that between 2021 and 2030, we will have an increase of $600 billion to more than 1 trillion. And where is the increase coming from? Well, the increase is mostly coming from 3 important areas: computing and data storage, wireless communication, automotive, electronics. Those 3 are good for the 70% increase that we may expect in 2030 compared to 2021. At the same time, of course, you have a lot of spending in new fabs. Also, the equipment market is strongly increasing. In 2021, the equipment market for wafer equipment was good for about $100 billion, where about 20% of that budget went for lithography, 15% for CVD, 22% for etching, and about 5% for metrology. And if you look at the important equipment vendors, and I'm not going to read them, I don't want to make publicity for some companies, but you see that the 4 top companies are getting a very huge spending every year, more than $12 billion per year. That's a huge amount. And you can ask the question, where is the money going to? Where are they building all those fabs? Well, if you look what happened in 2021, then you see that about $30 billion of the $100 million went to China. About 25 million went to Korea, also about 25 to Taiwan, and then Japan. So a lot of the spending in 2021 was happening in Asia. And in the coming years, we are expecting that the high amount of the spending in semiconductor equipment will go to the US with all the new fabs, and also to Europe, because due to the European Chip Act, the European Union expecting to expend more than 45 billion.
Professor Korklais. Professor?
Meter technologies, we can look at the forecast.
Just a minute. Professor, just a minute. You have a problem with your audio. Please close your screen to see it's become better. Close your video.
Close.
It's only to see your audio to be better.
Okay, I will.
Yes.
One moment. No. I'm trying to close it. If I can find it.
There is a hand symbol, Professor Clays.
Yeah.
And adjacent to that, there is an option of switching off on the left hand side. No. On the left hand side of the hand symbol, yeah.
On the left hand side, yes. It's.
Oh yeah. Okay, there I see it.
Yes.
Yeah.
And yeah, maybe if you can also hide your toolbar. There is a toolbar. And if you can. When you will put it in the presentation mode, there is a toolbar which is there.
Yeah. Okay.
So,
is that better?
Yes, it's better.
Okay.
Okay.
So I was saying, in order to get a good feeling about how important are the sub-10 nanometer technologies, you can see at the installed capacity. And here you see a bar chart with the installed capacity from December 2019, December 2020, up to the expectations of 2024. And you see, for instance, on the top, the red one, are the large technologies. That means larger than 180 nanometer. And where the share was about 24% in 2019, that will go down to 18% by 2025. But if you go at the bottom, the blue area, there you see that the smaller than 10 nanometer technologies will increase from 4.5% up to 29% or 30%. So that means those technologies are gaining more and more importance. And we can have another view on that by looking at the revenue of one of the important semiconductor players, TSMC. If you look at Q1 2021, last year, there was a revenue of $17 billion, which was a 35% increase compared to 2020. And if you then look at the pie chart, you see which of the technologies was bringing the revenue. And there you see that 7 nanometer was giving 33%, 5 nanometer was giving 8%. That was the data in 2020. If you look at 2021, then we see that the 7 nanometer is 31% and the 5 nanometer 19%. So that means that about 50% of the revenues was coming from the 7 and the 5 nanometer technology nodes. And also in the last quarter of 2021, there was even a strong increase of the 5 nanometer technology node. So that means the importance of 7 and 5 nanometer is strongly increasing every year. Now, we had already a view by Professor Rinani about scaling. And the first way that we did scaling was what I would call geometrical scaling. That means we were following the law of Bob Denard, and we were scaling all the different horizontal and vertical dimensions, and also some of the key parameters, like, for instance, doping concentration. That was working very well till about the middle of the 90s, when we were entering the 1 nanometer technology. And then we noticed that the scaling was going faster than the geometrical scaling. And that means we have to switch over to a different approach, which I would like to call a scaling of the material and the devices. And that means we went over in device architecture from planar to FinFET to gate-all-around. And in parallel, we were using a lot of new materials in order to cope with the needed scaling to get the needed performance and area density. And in 2007, for instance, you see that Intel introduced the high-K materials and the metal gate. And you need that because if you don't introduce high-K, metal gate, and strain engineering and all those different process options, you see that you would remain with the blue. The blue here in this view graph is a classical scaling. And you have to do something to the processing options in order to come over to a better scaling. I will change my laser pointer, yes. After material and device scaling, we go over to what is called circuit scaling. We put more different dies in a package, and we are going to put different wafers or dies on top of each other. And finally, we are going to come to scaling at the architecture level. So we do what we call system scaling. And all that is needed in order to keep in trend with loss-more. And here you see, you have seen that already before, that loss-more means that we are scaling down in dimension. You see the dimension of the different nodes, and we go from scaling devices to scaling basic logic functions, finally ending up with system scaling. And in combination with what we call more, making a higher packing density, we are also using more than more. That means we are also using options in order to increase the functionality by, for instance, using photonic integration, by using bionic applications, things like that. Here you see some recent data from Apple, where for the Apple Mac Studio desktop, and I'm not making publicity for Apple, although it's a good piece of equipment, they're using the M1 chip. They have the M1, the M1 Pro, the M1 Max, and now the latest one is the M1 Ultra. The M1 Max got 114 billion transistors. And for the M1 Ultra, they are using 2 M1 Max chips, allowing them to handle more than 10,000 signals and switching over to 2.5 terabyte per second, giving a very large bandwidth. But more important, if you do a comparison between the M1 Ultra, this one, and the classical 16-core desktop, you see a 90% improve in performance. So that's the reason why, for their more recent products, Apple switched over to TSMC instead of Intel. At the same time, if you do a comparison between the M1 Ultra and the high-end CPUs, you see a 200-watt lower power consumption. And you have heard that already in the previous presentations. Power consumption is extremely, extremely important. We have to do whatever possible to lower the power consumption as much as possible. Now, for the moment, there's a huge evolution in Internet of Things. And if we look at what happened the last 10 years, if we go from 2015 to a prediction to 2025, we see that there is an increase from 15 billion devices up to 75 billion devices. And to my opinion, the predictions here are still rather negative. It will be much higher than what we are expecting. So that means that now in the coming years, we are going to see that there are trillion sensor devices needed and coming on the market. those type of devices will become part of our everyday life. All that is now strongly driven by the 5G applications, which we need for enhanced mobile broadbands. We need it for mission-critical services, and we also need it because of the massive IoT applications like wearables, smart homes, smart cities. Everything is becoming smart. And that means we are going to find Internet of Things in all the different industrial areas. Whether we are speaking about entertainment, but it's obvious that we are using Internet of Things. We will also find it in safety, in agriculture, we'll find it in retail, we find it in medical applications. So that means 5G is creating new values and giving a real redefinition of our industries. And semiconductor technology is also needed to solve the main human challenges, like we have the climate crisis, the pollution, the healthcare sector, and of course, hunger in the world. So we will not be able to handle these humanity challenges without the strong innovations and improvements in the semiconductor technology. So what is the evolution? We are still working with Moore's law in order to get scaling for induced density, high functionality, and a lower manufacturing cost. I mentioned already the 2 nanometer technology of IBM, the 3 nanometer of TSMC. In addition to that, there's a strong increase in increased functionality and system on a chip. We will do 3-5 integration on silicon, gallium arsenide, indium gallium arsenide, gallium nitride, and I will come back to that later during my presentation. And we got an explosive increase of new application fields, like automotive, healthcare, quantum computing, and so on. And we are going to do co-integration of the classical semiconductor devices with a different functionality, like imagers, detectors, LEDs, and lasers. Let's now have a look at what is the evolution of advanced silicon devices. And we know that we went from the planar device to the 3-dimensional device, the FinFET. We switch over to multiple FinFET applications. Then we go over to nanowires. And finally, from the nanowires, we switch over to stacked nanosheets. But here you see an example of IBM 5 nanometer technology. But that's not the end. For the FinFET, the gallium arsenide nanosheet, we'll go over to the Forex sheet. The Forex sheet is a device where we want to place the N-channel devices and the P-channel devices as close to each other as possible in order to save area. And we do that by using what we call a dielectric isolation. And in that way, we can still increase the packing density and increase the performance and get a better control about the gate. And at the same time, we have to see that we can control the variability, because that's one of the problems. If we are switching over to new device structures, in many cases, we are losing variability, and we have to solve that problem. Here you see an image of work from IMEC, published last year, where they were doing a co-integration of a fork structure, here on the left, together with a nanosheet FET. And you can see that by optimizing the technology, because if you don't optimize the technology, you got a lot of under edge and you get less well-defined structures. But by optimizing technology, you can get both for the N and the PMOS devices a slope in the order of 68 millivolt per decade. A step further from the fork structure is to use a different approach to solve the problem of the N and the P-channel devices. Instead of having the N-channel and the P-channel devices next to each other, you can put them on top of each other. In that way, you get more functionality for the same area. And that is called a complementary FET. And that's the way in which people will go to the 2 and eventually the 1 nanometer technology nodes. Here you see an example from a CFET technology where you have the bottom Cmos FinFET devices, on top of which nanosheet NMOS devices are fabricated. And both devices, the bottom FinFET and the top nanosheet devices, got the performance that you are expecting from them. So that's the way to go. Go from FinFET to gate-all-around to nanosheet, for nanosheet to nanophoric devices, and for nanophoric devices to CFET technology. But that's working on what we call the architecture of the device. But that's not the only thing in which you can solve the scaling problem. At the same time, you have to work at the technology. And I mentioned already that in 2007, 2008, Intel was using stress engineering, IK metal gate, IK dielectrics and metal gate in order to fabricate their devices. Well, the more you're shifting to different type of devices, the more you will have to work on other processing options. That means you have to introduce ultra-low K dielectrics. You have to look at other barrier material. You can implement air gap devices. You have to work with different concepts for Damascene. You have to replace the copper, the copper metallization, for instance, by ruthenium metallization. You can work with barrier power rails. So that means you have to do a lot of work on using the optimized technology options, combined, of course, with the progress in lithography. Now, below the 7 nanometer technology nodes, you need extreme UV. Deep UV is not going to do it anymore. Or you have to go over to multiple processing steps, but that's making fabrication extremely expensive. So from a cost-effective point of view, you have to use extreme UV. And if you want to scale down further to the 3 nanometer technology, you will have to use extreme UV together with high numerical aperture lenses. Also in the memory device, and we have heard that already in the previous presentation, there are quite a lot of different options, from speed torque transfer, magnetic, random access memories, to phase change memories, to resistive random memories, conductive bridge random memories, ferroelectric. So there is also a roadmap in order to cope with the density that is requested. The density which have to be done in line with the possibilities of scaling, and keeping in mind, of course, the overall cost of the final memory, because the cost must be lower and lower while you increase the density. Here, for instance, you see the evolution between 2019, that's the top, and 2021, the evolution by 4 different NAND memory manufacturers. For instance, if you look at SK Hynix, you see that for 32 gigabyte, they were using 71 square millimeter. In 2021, they only use 65 square millimeter for the 64 gigabyte. And if you use the technology proposed by Micron, they go from 57 even down to 59. So this is the evolution that's happening. Different concepts for building your device in order to increase the density and in order to lower the cost. Of course, everything starts in 47 with germanium devices. And about 15 years ago, people became interested in using again germanium because they wanted to increase the mobility of the devices. And increase in mobility, you could do that by switching over from silicon to silicon germanium. But if you still want a high mobility, you can switch over to germanium. But of course, you cannot work with pure germanium. You have to work with germanium on silicon. But in order to use that technology, there are different challenges. Like, for instance, you have to work on passivation. You need a very high quality gate stack, what is already difficult on silicon and silicon germanium, but even more difficult on germanium. The contact technology for germanium is quite different than the contact technology for silicon. And of course, you have to do integration on the silicon platform. That means you are going to use epitaxial growth. And that means you have to control the defect density. However, notwithstanding the challenges, good devices have been fabricated. And here you see one of the first devices, planar devices, that were fabricated by Intel, Polarizetti, where they have been using a stack of different buffer layers in order to end up with high-quality germanium devices for quantum well applications. Over the years, people have been realizing planar germanium devices, FinFET devices with germanium. They have been working on TFET devices. You can have full germanium TFETs or only germanium in the source. And people are also using germanium for nanowires. Germanium, where you have a silicon capping layer around your germanium core. So different type of devices have been fabricated and demonstrated. Here again, you see the cylinder germanium for FinFETs. As already mentioned, you can also use 100% germanium for a FinFET. And in the figure on the right here, you see data coming from TSMC and the green dot data from IMEC. And you see that in both cases, excellent performance have already been achieved. And that was in 2014. So now we are 2022. You can also use germanium with some tin in order to make gate-all-around devices. Small amounts of tin, order about 1%, in order to increase the performance. As already mentioned, you can use germanium in the source of the TFETs. Next to the advances in silicon devices, there is a lot of advances on 3.5 devices, but I want to focus mainly on 3.5 on silicon. If you do 3.5 on silicon, you have to do epitaxial growth. But the problem is, if you work with silicon and you work with, for instance, indium gallium arsenide, there is 8% mismatch between silicon and germanium. That's too much, and that's going to give you a lot of defects. In order to solve that problem, you can use buffer layers. You can use, for instance, a germanium buffer layer, which is only giving a mismatch of 4%. And then under germanium, you can grow, for instance, the indium gallium arsenide or the indium phosphide layer, which is also giving a mismatch of about 4%. But defect control is quite important. And you can grow a full epitaxial layer on a silicon wafer, but for many applications, you only want germanium in dedicated areas. And you can do that by what we call the use of narrow trenches. You have narrow trenches where you remove the oxide, and in the trench, you're growing the germanium. And the amount of defects, and the dislocations, the track dislocations, and the stacking faults that you will have in the trench will depend on the width of the strand of the trench and on the aspect ratio, the height to the width. And by optimizing that, you can make germanium layers where the defects are remaining to the interface layer. And that means that in the top part of the layer, you can grow your real devices. A variation of that is what we call nano-rich engineering. That means you start with a shallow trench where you're growing germanium, for instance, and then on top of that, you're growing your other material. That means you're controlling the defects by the aspect ratio. You can control the amount and the type of defects, and you can use that, for instance, for growing gallium arsenide on silicon with a germanium buffer. You can use that to grow gallium antimonide, or you can even use that to grow indium gallium arsenide. You have different options in order to make 3.5 devices on a silicon substrate. And here you see some 300mm indium gallium arsenide FinFETs produced by TSMC with very good electrical performance. On this view graph, we give you some indium gallium arsenide FinFETs with a gate length of 20 nanometer, manufactured by IBM and Samsung, with again excellent performance. You can also work with indium gallium arsenide Mosfets. This is work from IMEC, where they are achieving 3,500 square centimeters per full second mobility and a subthreshold swing of 71 millivolt per decade, which can be further optimized by optimizing the gate dielectric. Excellent performance has been obtained by IBM Zurich, where they have been fabricating 13 13 nanometer devices, but instead of using epitaxial growth, they have been using wafer bonding of indium gallium arsenide, indium phosphide on silicon. So in general, there are two approaches. As already mentioned, you can use epitaxial growth or you can use wafer bonding. Of course, if you use wafer bonding, you have to keep in mind that there are some drawbacks. With wafer bonding, you are growing full wafer on top of each other. That means you cannot make those type of devices in selective areas. And of course, if you want to do wafer bonding of an indium phosphide wafer on silicon, the problem is that you cannot find very large indium phosphide wafer substrates, that you are limited in the size of the wafers you can bond together. Was not the case if you work with an epitaxial technique. And there's an older example where people have been integrating indium gallium arsenide FETs together with gallium arsenide, aluminum gallium arsenide lasers. This is done by epitaxial growth, and it's work performed by the National University of Singapore and MIT in the US. So this is really demonstrated that you can have a huge variety of different applications by using that type of processing, using 3-5 materials on a silicon substrate. Nowadays, there's a lot of interest in 3-5 nitride technologies, and I want to spend a few slides on that. If you look at the differences between silicon, the blue, silicon carbide, and gallium nitride, and if you make a comparison between the band gap, the mobility, the saturation velocity, and the breakdown voltage, then you will see that with gallium nitride, you can get high voltage, high power, high frequency, and very efficient light emission. And for lighting, you need long lifetime, robustness, a high energy efficiency, small size, and of course, you should avoid any toxicity. So that means that gallium nitride is very, very useful for lighting, but also for power applications, where you have to handle high voltages and high currents. And quite important is the under-resistivity. The lower the under-resistivity, the higher the breakdown voltage. And here you see the differences between silicon, silicon carbide, and gallium nitride. And nowadays, gallium nitride is reaching already very close the limits. If you look at the devices that has been reported, those are different devices reported in the literature, that you see that the devices are performing better, much better than the silicon limit, and coming very close to the gallium nitride limit. But of course, if I speak about gallium nitride, I refer to gallium nitride on silicon. But that's not the only technology. If you look at gallium nitride, you see that if you look between the year 2000 and 2025, you're expecting a 10 times growth in only 5 years. So the market will strongly increase. This is gallium nitride power devices, gallium nitride. But if you speak about gallium nitride, there are two competitors, although I don't call them competitors, but because they have both different applications. You can use with silicon carbide, gallium nitride on silicon carbide, where you see there's a strong increase. By 2026, you will have about $3 billion market, where an important part of the market is taken by automotives. And that's also represented in this view graph, where you see a strong increase in the market of gallium nitride on silicon carbide for EV and HEV applications and charge infrastructures. And in the near future, also high power will become an important, power applications will become an important part of the market. At the same time, we see that there's a strong evolution also in gallium nitride on silicon, where if you look at the forecast for 2026, we are expecting more than $1 billion. So that means about $3 billion for silicon nitride on silicon carbide, about $1 billion for silicon nitride on silicon. And if you look at the evolution of the RF silicon carbide and silicon nitride market, you can see here the green line. This is the evolution of the gallium nitride on silicon carbide, but you see that nowadays the silicon nitride on silicon is strongly coming up. And in the coming years, there will be, I would say, an equal market share between gallium nitride on silicon and gallium nitride on silicon carbide. I am referring to equal market share. I am not saying that one will take over the other, because as already mentioned, we are speaking about different applications for silicon carbide and gallium nitride. There are different applications, but there are challenges. That means you're looking at large diameter substrate, you want to have a low defect density, you want to have a good passivation, and you want to have a good uniformity and reproducibility. And that means that I'm mainly referring here to making epitaxial layers on silicon in order to be able to work with large substrates. If you look at the gallium nitride devices that has been reported in the recent years, you see that we have gallium nitride nanowires on a sapphire substrate. We have gallium nitride TFETs on N-type gallium nitride, and we also have gallium nitride nanowires on 111 silicon. So that means the different type of devices have been produced, and the feasibility of those type of devices have been demonstrated. If you think about other devices, you can work with Mosfets, where we are looking at enhancement mode devices with a low leakage, but you have to keep into account that you can have problems with the interface. You can look at high electromobility devices, where we have a high performance, but we are working in the depletion mode, and we can have high leakage. And we can have a combination of the two, the MOSFETs, where we have both a gate oxide and we have contact with the gallium nitride channel. In this case, we have a low gate leakage and high performance. So 3 types of devices which are being evaluated in order to end up with the highest performance that is needed for the different type of applications. 2 years ago, people have been reporting a T-gate gallium nitride high electromobility device on silicon with excellent performance, an Fmax of 204 gigahertz and an FT of 250 gigahertz, which is very good for gallium nitride. It's not the best performance for gallium nitride, because if you have gallium nitride on silicon carbide, you can obtain values around 450 gigahertz for both FT and Fmax. But if you make a comparison between the FT versus the device length, if you see the blue data is the data for gallium nitride on silicon carbide, and the red data is the data for the frequency performance of the gallium nitride on silicon. And you see that there is a lot of improvement for the frequency performance of the gallium nitride on silicon devices. Slowly they are coming closer and closer to the performance of the gallium nitride on silicon carbon. There are nowadays many companies working on gallium nitride. The market size in 2020 was about 1.6 billion and is expected by 2027 to go up to about 6 billion. That means a growth rate of about 20%, and more companies are also opening now gallium nitride facilities, because I would say the market is really exploding. Together with that, of course, there is a strong expansion of the equipment. Here you see the equipment for MOCVD, for gallium nitride, the yellow one, gallium nitride LED, the orange one for gallium nitride power devices, and the brown one, this one here, for gallium nitride RF devices. And you see a strong part of the MOCVD equipment is dominated by gallium nitride devices, where also the market share of the silicon carbide devices and the gallium arsenide devices is increasing. Finally, I would say a few words about 3D sequential integration. In order to increase the packing density, you can put more dies in the same chip, or you can put more wafers with chips with different functionality on top of each other. That means you can do die-to-die packaging in 3D dimension, or you can do wafer level packaging. That means you can go from classical CMOS or beyond CMOS, on which you're putting a level with memories, for instance, and on top of that, you can make some analog or RF devices. So here you see an example, a recent example of CMOS at the bottom, where in this case using wafer bonding, they have been using a microprocessor core devices and memory cache coming to a 3D integration with a high packet density. So that means you can do something at packaging level, you can do die or wafer level, or, and that's what I want to mention now, you can do what we call sequential 3D integration. That means you're processing one level of devices, then you put another level, and in the level on top of that, you're going to build different type of devices. And the second layer in which you're going to build your devices can be achieved by either epitaxial growth or by wafer bonding. You can put, for instance, resistive RAMs on CMOS in that way. So that means you're doing processing of the bottom level, you put a layer on top, process of the bottom level, you put a layer on top, and then you're doing the processing in the top layer, and you're forming a context. In this way, you get a higher pitch than through silicon vias, you get a higher contact density, and the alignment is done by lithography in this case. That means that in each of the different layers on top of each other, you can optimize the different type of devices. You can have different strain engineering, different gate oxidation, different channel materials, devices with different architecture. By putting the device on top of each other instead of next to each other, you're going to get a lower wire length between the devices. The only problem is, of course, you have to control the temperature processing that you are using for fabricating the devices in the top layer. Here, for instance, you see the sensitivity of cobalt and of tungsten, and you see that you got a much better performance of your devices if you are using, for instance, cobalt. So that means you have to lower the temperature budget when processing the top wafer devices. At least if you use the epitaxial approach. If you do wafer bonding, then of course you're free with the temperature that you're using for the top and the bottom wafers. So you have to control the bottom and the top dielectrics, you have to optimize the devices, and as already mentioned, there are two approaches for doing the layer transfer. The different approach is quite important for the dopants, because if you want to bring dopants in the top layers, you're using ion implantation. And if you use ion implantation, if you use, for instance, silicon top layer, you have to use high temperature in order to get an activation of the dopants and in order to anneal the defects. Here you see an example of IMEC, where they have been using bottom FinFET devices with junctionless FinFET devices on top, where they have first done the processing of the bottom devices, then they had a SOI donor wafer, where they did the dopant activation at high temperature, they did the wafer bonding, and then at low budget, lower than 500 degrees centigrade, they have been fabricating the top level devices. This is work from Stanford, where they have been using silicon bottom layers, on top of which they have been using 2 layers of resistive memories, and on top they have been fabricating a carbon nanotubes. And they are able to select the transistor of either the bottom layer in silicon or a select transistor of the top layer, the carbon nanotubes. So, and in that way, they have been making a system where the maximum temperature processing was lower than 200 degrees centigrade. If you use wafer bonding, you have to be careful with the misalignment. This is wafer bonding done by Yancy memory technology, which they have been using for a 120 layer 3D NAND, where you see here that there's a small misalignment between the 2 copper layers. At the bottom, you see some of the very recent results from a 120-layer 3D NAND from Hynix, where not only one, but they have been using 2 different layers of NAND arrays. So they had the bottom silicon devices with 1 wafer using NAND arrays and a second wafer on top of that with other NAND arrays. Here's a very nice heterogeneous integration of bottom gallium nitride devices, which have been fabricated as illustrated here. Then there's a second donor wafer, a silicon wafer, which they have been by wafer bonding connected to the processed gallium nitride wafer. And then they'll be processing devices in the top layer. So in this way, they have 100% monolithic heterogeneous integration of gallium nitride on silicon. What do I want to give you as takeaways? Well, 5G is there, and 6G is in the research phase. Advanced devices on silicon, germanium, and 3.5 materials all studied, and the results are very, very promising and will be there very soon. 3.5 materials on the silicon platforms like indium phosphide and gallium nitride are entering the market. Challenges remain the defect control and the quality of the gate oxides. 3D sequential integration has a huge potential for cost-effective manufacturing of system on a chip. But as already mentioned, you have to control the temperature budget. I had no time, I had to skip the slides, but 2D materials are gaining a lot of importance and will be coming. And also devices for quantum computing, artificial intelligence are gaining more and more importance and should be watched very carefully. Main question that you will be asking me is maybe, are we coming to the end of Moore's law? I would say no, not yet, but innovations are needed. And that's why we need good engineers and a lot of good research students. Moore's end is a basic for the economic fabrication of high-performing chips. But we have to take into account limitations to lithography. That means we have to use a different type of lithography in the future. We have to look for new materials, and we have to come over to advanced device architectures. As I mentioned, where we have the switch from a planar device to the complementary FET devices. There is a memory wall. The speed of the devices cannot cope with the speed of the systems that are needed. And a problem there could be the speed of the interconnect systems. So a lot of innovation will be done. As already mentioned by the previous speaker, we have to do something at the power wall. The power consumption is going to kill us if we don't work on new device architectures or look at new materials in order to keep the power under control. Quite important, we have to look at the sustainability. It was also mentioned already by the previous speaker. We have to look at power, performance, area, cost, and I would also say environment. Those 5 elements have to be into account. In the near future, we have to see for the new fabs how we can reduce the water consumption, how we can minimize the electricity, and very important, how we can do something to the CO2 print. The CO2 emission should be as low as possible for the future fabs, and people are working on that. And one final remark is, I would like to mention the concept semiverse. Semiverse is something like a new semiconductor metaverse. Metaverse, I hope you're familiar with that, is where you're living in the digital world, where everything is connected digitally, and you got a type of avatar controlling everything. Well, Dr. Arsha from LAM has been proposing that we should work at a universe where different enterprises, manufacturing sites, research lab, equipment manufacturer should work together in a difficult world in order to optimize the chips, the content of the chips, the equipment, the processing, in order to come to an optimized technology. An optimized technology which we can optimize to a large extent without the need of doing the fabrication. And in that way, we can control or minimize the overall cost. And of course, we can also keep into account, as already mentioned, the sustainability aspects. Internet of Things, we only have seen the tip of the iceberg. We are going to see many, many new applications in the coming years, applications that we are not even aware of, that they will be implemented in our everyday life. Thank you. Obrigado.
Thank you very much, Professor Corclais. As soon as you turn off your video, everything goes well, no problem with the internet. Ele saiu? Okay, I think Professor Corclais not only stopped his presentation, but only his Google Meet session. I'll just wait for some minutes. I have some questions for him. Let me see. I put here again our okay. We just finished now the last presentation of this mini colloquium, and I'd like to thank.
I'm back.
Oh, great! I worry about you. What
I'm not running away and nothing like that.
Okay, Professor. We have some questions here from the audience, from the YouTube. Let me first ask you for the first question. What take in consideration the scenario that you showed to us, what do you think about 2D device?
I'm thinking about the question. You mean the classical 2D devices?
Yes.
Compared to, for instance, the 3D, the FinFETs and that type of devices?
Yeah, for application, for real application.
Oh no, the 2D devices will remain there. I forgot to mention that when I was given an overview of the revenue of, for instance, TSMC, I was focusing on the 7 and the 5 nanometer technologies. But on the same slide, there was also 180 nanometer technology and then 130 nanometer, 90 nanometer. I mean, those type of devices, those type of technologies will remain. We need them. If you think about your smartphone, if you would open your smartphone, please don't do it. If you would do that and you would look at the different type of devices, you will see that for the very advanced devices, there are very old classical devices in it. So they will not disappear. The only thing is that with the 2D devices, your limit in how far you can go in scaling. That's the only thing. But you don't need the scaled devices for everything. Lucky for that.
Okay, Professor. Now you have questions. May you have a look in your chat? Okay, have a look your chat.
I cannot see the.
Let me show you.
I cannot see the question, so.
Okay, now.
Maybe they are coming in one moment.
Bruno. And
okay, no, yeah, Bruno. Okay, I got a first question here regarding gallium nitride, MOSFETs. What are the main strategies being used in order to achieve anomaly on device? Is defect reduction in the gate insulator the main approach? Yes, in my opinion, is one of the key things you have to control. If you cannot control the defects, you are not going to get devices with the required functionality. several parameters. Even, for instance, your 1/f noise will be influenced by the defects in those layers. I would say for all 5 type of activities on silicon, defect control remains the most important issue. Will you be able to come to a 0 defect level? The answer is no. The only thing you have to do is to try to remain the density below the level where you see an impact on your device performance. That's the thing you have to do. Is that answering a little bit the question?
Yes. Yes. There is one. You are seeing the question?
I see the same question coming back a few times.
Okay.
Maybe
The last two questions. The last two. I can read for you. Eh? What do you think are the main challenges and opportunities in the research of gallium nitride Hammett and Ms. Hammett?
Well, the main opportunities is that if you go over to gallium nitride type of devices, that you can come up with different applications. I say many people are always saying one device is competing with another device, and when will one device be replacing the other device? When I was a young student a few years ago, quite a year ago, the question was, when is gallium arsenide to take over from silicon? The answer is straightforward, never.
Never.
Because each of those technologies got their specific areas. And only in a few areas, they are competing. For instance, if you would say 25 years ago, high-speed CMOS will never be realistic. People would say, yes, you cannot do that. If today you look at the high-frequency performance of CMOS, you've got very high frequencies. So that means some of the applications are becoming competition. But then at the end of the day, who is the winner in those cases? Well, the device or the devices who can do what you want, give you the performance you need, and at a cost, the low possible cost. The lower the cost, the more you will take out of the market.
Okay.
And the challenges are indeed that we have to learn to work with those new materials. And indeed, defect control is one of them, but there are other properties, growing high-K dielectrics on gallium nitride oriented devices is not so easy as doing that on silicon. So we have to control the amount of interface. So interface density is important. What Professor Hiroshi mentioned in the beginning, the leakage currents, you have to control them, and then they will be different if you work with different materials. Contact resistivity. Not easy. Yes. People were believing that a long time ago, contacts on gallium arsenide were easy because they were using gold. And yes, I was given good performance, gold contacts on gallium arsenide. But nowadays, nobody wants to use gold. So that means people have to look for what we call gold-free contact technologies. So in all of that are challenges. But there's a lot of innovation, and there's a huge amount of research going on by different groups. And I think that's very important that different groups are looking at that, and of course, wherever possible, working together in order to jointly solve the problems. Because each of the problems in technology are very, very huge, or very, very large. Where 20 years ago, people were saying, oh, I will do research to come up with a new dielectric that will replace silicon dioxide, and that will be useful for the coming 15 years. Nobody was able to do that. And people have been looking everywhere. Europe, Asia, the US, on different type of high-K dielectrics. and depending on the type of application you want and the specifications, you will use a different approach.
Yes, true. This means you have a lot of work for the student, for the professor in microelectronic and nanoelectronic field, right, Professor?
Yep, that's right. But the good thing, and that's what I ended, maybe it was not clear to everybody, I ended the last sentence on my slide was that you can do a lot of work in a digital environment. So where people say, oh, I'm not going to work on technology anymore because I don't have access to processing facilities. I don't have, I don't know, $200 million to upgrade my fab. That's right. But you can do a lot of work by simulating. There are excellent simulators around now. Where you can do, indeed, you can do technology in your office, in a way of speaking.
Yes. The metaverse.
Of course, the final proof will be by eating the pudding. At the end of the day, you will have to do real fabrication, of course. But you can do a lot of excellent research.
Okay, Professor, thank you very much. Now, for your presentation, now I'm just show the last slide for closing the mini colloquium. Just a minute.
And then we are getting free caipirinhas.
Exactly. Next time you come to Brazil, free caipirinhas. Okay. Now I would like to thank you, Professor Korklais, also Professor Hiroshi, Professor Manoj, Professor Elena, for the all excellent talks. The good thing in this team that everyone talk different aspects of the evolution of the technology. That I think was very good for the audience. You have a lot of students, professors, and then can see different things of each talks. Thank you very, very much. It's really a pleasure for me to present this mini colloquium. Thank you for all of you to stay with us till now. And I hope you can repeat this mini colloquium in the future here in Brazil. And thank you very much for everyone, for the speakers, for the audience, also for Paula Gopian, who helped me with the organization of the mini colloquium. And everything will be available on the YouTube. If someone miss a part of the talk, you can look and can see again if you think to be a good thing for you. Okay, thank you very much for everyone, and see you next mini colloquium. I hope soon. Bye-bye.
Okay.
Thank you.
Thank you.
Thank you.
Bye-bye.
Bye-bye.
Bye.
Bye-bye.